hushed silence of deep space, where stars burn against endless black, a question has always haunted humanity. Why is there something rather than nothing? Why does existence exist at all? Look up at the night sky. Feel the cool air against your skin. Listen to your heartbeat. All of this, from the vast cosmic webs of galaxies to the atoms dancing in your cells, emerged from somewhere, somehow. But from what and how? For thousands of years, we assumed the answer must involve a creator, a first cause, something or someone outside our universe that set everything in motion. It seemed the only logical conclusion. After all, in our everyday experience, things do not simply appear without cause. Houses do not build themselves. Books do not write themselves. Children do not raise themselves. Yet, as we peer deeper into the foundations of reality, as our instruments detect the faintest whispers from the cosmic dawn, as our mathematics stretches to describe the very fabric of existence, we find ourselves confronting a possibility both profound and unsettling. What if the universe needed no external cause? What if, in ways almost too strange for human minds to grasp, the cosmos could emerge naturally, inevitably, perhaps even necessarily, from principles embedded within itself? This is not merely a scientific question, though science will guide much of our journey. It is not simply a philosophical riddle, though philosophy will help us frame what we discover. It is perhaps the most fundamental mystery we can contemplate, where the boundaries between knowledge and wonder dissolve. As we explore, we will walk the razor's edge between what we know and what we can only imagine. We will confront the limits of human understanding and peer beyond them. We will encounter ideas that challenge our intuitions about how reality works. What is time, really? What is nothingness? What are the laws of nature, and where do they come from? The 20th century revolutionized our understanding of the universe. Einstein showed us that space and time form a single fabric that can stretch and bend. Quantum physics revealed that at the smallest scales, reality becomes fuzzy, probabilistic, almost dreamlike. And observations of distant galaxies taught us that our universe is expanding, cooling, evolving from a hot, dense beginning some 13.8 billion years ago. But these discoveries only deepen the mystery. If time itself began with the Big Bang, what sense does it make to ask what came before? If quantum mechanics tells us that particles can appear from nowhere, briefly flickering into existence before disappearing again, could a universe do the same? If the total energy of the cosmos, adding matter's positive values to gravity's negative pull, equals precisely zero, did creation require any energy at all? As we grapple with these questions, you may find comfort in certainty or in mystery. Some will see divine purpose, where others see natural processes. Some will embrace the strangeness of a self-creating universe, while others will seek more familiar explanations. This exploration makes no claim to final answers. Instead, it invites you to wonder, to contemplate the fragile miracle of existence itself. The fact that we exist at all, that conscious minds evolved within this universe capable of pondering their own origins, is perhaps the greatest mystery of all. Our journey begins not with certainty, but with curiosity, not with answers, but with better questions. So let us start where science has brought us most confidently, with what we know of our universe's history, before venturing into more speculative realms where the universe's self-creation might be found. In the darkness between stars, in the quantum foam of empty space, in the mathematical symmetries that govern reality, we may find clues to how everything, perhaps, came from nothing. And in that search, we may discover that the line between scientific curiosity and existential awe is thinner than we ever imagined. Our story begins with what we know most confidently. The evidence tells us that our observable universe is approximately 13.8 billion years old. This is not a guess or speculation. It is the result of multiple independent lines of evidence that converge on this same answer with remarkable precision. When we look out into space, we are looking back in time. Light from distant galaxies takes millions or billions of years to reach us. The furthest objects we can see appear to us as they were when the universe was young. And when we look to these cosmic horizons, we find something extraordinary. In all directions, if we look far enough, we discover that the universe becomes simpler, hotter, and more uniform. Galaxies appear younger, and less structured. The elements become less diverse, dominated by the simplest atoms like hydrogen and helium. Everything points to a beginning, a moment when the cosmos was compressed into a state of incredible density and temperature. But our most compelling evidence comes from a faint glow that permeates all of space. The cosmic microwave background radiation. This gentle warmth, just 2.7 degrees above absolute zero on the Kelvin scale, represents the oldest light in the universe. It began its journey when the cosmos was only 380,000 years old, when the universe first became transparent enough for light to travel freely. This ancient light tells us something profound. It shows us that the early universe was remarkably uniform, with only tiny variations in temperature, about 1 part in 100,000. These minuscule differences, like wrinkles in cosmic fabric, were the seeds from which all structure in our universe would eventually grow: the galaxies, stars, planets, and eventually, ourselves. When we measure the cosmic microwave background with exquisite precision, as we have done with satellites like WMAP and Planck, we find patterns that reveal the age, composition, and geometry of the cosmos. These measurements allow us to rewind the cosmic film, mathematically tracing the universe back to its earliest moments. Another pillar of our understanding comes from observing that the universe is expanding. In the 1920s, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and the farther they are, the faster they recede. This was not because we occupy any special place, but because space itself is stretching, carrying galaxies apart like dots on an inflating balloon. When we measure this expansion rate and project it backward in time, we arrive again at a beginning, a moment when everything was compressed together. This convergence of evidence gives us confidence that the universe as we know it had a starting point, what we call the Big Bang. But the Big Bang was not an explosion in space. It was an expansion of space itself, beginning from a state of extreme density and temperature. Every point in our current universe was once part of that initial state. There is no center to the expansion, no special location where it all began. The beginning happened everywhere at once. After the initial expansion began, the universe followed a remarkably ordered sequence of events, a cosmic recipe that we can reconstruct through physics and astronomy. For the first few minutes, the universe was so hot that atomic nuclei could not form. The cosmos was a sea of energy, with particles and antiparticles blinking in and out of existence. As it expanded and cooled, protons and neutrons could combine to form the nuclei of the lightest elements. This process, called Big Bang nucleosynthesis, produced primarily hydrogen and helium, with traces of lithium, in proportions we can measure today. The match between theory and observation is one of the triumphs of modern cosmology. For hundreds of thousands of years after this, the universe remained too hot for atoms to form. Light could not travel far without scattering off free electrons, making the cosmos opaque, like a dense fog. Then, about 380,000 years after the beginning, the temperature dropped enough for electrons to combine with nuclei, forming the first atoms. Suddenly, light could travel freely. This moment of clarity produced the cosmic microwave background radiation we observe today. For millions of years after this, the universe entered what astronomers call the cosmic dark ages. No stars yet shone. The cosmos was filled with neutral hydrogen and helium gas, gradually clumping together under the influence of gravity. Eventually, perhaps 100 million years after the Big Bang, the first stars ignited. These cosmic pioneers were giants, hundreds of times more massive than our sun, burning hot and dying young in spectacular explosions. In their brief lives and violent deaths, they forged heavier elements and scattered them across space, enriching the cosmos with the chemical ingredients that would one day make planets and life possible. As time passed, galaxies formed and evolved. Colossal black holes grew at their centers. New generations of stars were born from the remains of their predecessors. Planets formed around many of these stars, including, eventually, our Earth. And here, on at least one small world, life emerged, evolved, and became conscious enough to look back and reconstruct this entire cosmic history. This is what we know about our beginning. This is the story written in the light of distant galaxies, in the atoms that make up every substance, in the cosmic background radiation that fills the sky. It is a story of expansion and cooling, of increasing complexity and structure, of matter organizing itself under the influence of fundamental forces. Yet as solid as this understanding is, it leaves the deepest questions unanswered. Why did the universe begin in this particular state? What set the initial conditions? What caused the expansion to start? What selected the laws of physics that govern everything from the largest galaxy clusters to the smallest subatomic particles? And most mysteriously, what happened at the very beginning? When we attempt to trace our universe back to its first fraction of a second, our physics begins to break down. We approach a boundary where space and time as we understand them may cease to have meaning. This is where our journey must now take us, into the first moment of creation, where science reaches its current limits and new ideas emerge about how a universe might create itself. As we venture into this territory, we move from established science to more speculative realms. But even in this speculation, we are guided by mathematics, by principles of physics, and by the remarkable consistency of the universe we observe. We are not abandoning reason, but stretching it to its limits, attempting to peer beyond the cosmic horizon to the moment of creation itself. Now we venture into the cosmic dawn, the first second of our universe's existence. This infinitesimal moment contains more drama, more transformation, and more mystery than all the billions of years that followed. To comprehend what happened during this brief instant is to approach the very edge of human understanding, where our mathematics strains against the limits of what we can verify or observe. Our journey begins at what physicists call the Planck era, the first unimaginably brief moment after the beginning. How brief? 1 Planck time equals approximately 10 to the negative 43 seconds. To put this in perspective, comparing 1 Planck time to 1 second is like comparing 1 second to the age of the universe, multiplied by a factor of more than 3 trillion. This is truly the frontier of physics, where space and time themselves may lose their familiar meaning. During this Planck era, all 4 fundamental forces that govern our universe today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single superforce. The temperature would have been incomprehensibly hot, approximately 10 to the 32 degrees Kelvin. For comparison, the center of our sun is a mere 15 million degrees. The density would have been so extreme that the entire observable universe was compressed into a volume smaller than a single proton. We cannot directly observe or recreate these conditions. Our most powerful particle accelerators can probe back to only about 10 to the negative 12 seconds after the beginning, still an eternity compared to the Planck era. What happened before that remains in the realm of theoretical physics, where mathematics and logical inference must guide us where direct observation cannot reach. The Planck era represents the ultimate limit of our current physical theories. At this scale, quantum effects dominate even gravity, creating a realm where both general relativity and quantum mechanics must apply simultaneously. Yet these 2 fundamental theories, each extraordinarily successful in its domain, speak different mathematical languages. General relativity describes a smooth, continuous space-time fabric, while quantum mechanics reveals a granular reality of discrete energy states and probabilistic outcomes. When we attempt to combine these theories mathematically, we encounter infinities and paradoxes, signs that a deeper theory must exist. This hypothetical theory, often called quantum gravity, remains one of the greatest unsolved challenges in theoretical physics. Without it, the first instant of creation remains shrouded in mathematical uncertainty. Nevertheless, theoretical physicists have proposed several frameworks that might someday help us understand this earliest moment. String theory suggests that the fundamental constituents of reality are not point particles but tiny vibrating strings, whose different resonance patterns correspond to different particles. The mathematics of string theory requires additional spatial dimensions beyond the 3 we directly experience, dimensions that might be curled up so tightly that they remain hidden from our observation. Loop quantum gravity, another approach, proposes that space itself has a discrete, quantum structure at the Planck scale, like a fabric woven from tiny loops. In this view, space is not infinitely divisible, but has a minimum possible size, a quantum of space. Time too might come in discrete units rather than flowing continuously. These theories remain speculative, but they offer mathematical tools for exploring how space and time might have emerged from a more fundamental quantum reality. They suggest that what we experience as space and time may be emergent properties arising from deeper quantum processes, much as temperature emerges from the collective motion of countless molecules. As we move beyond the inscrutable Planck era, approaching 10 to the negative 36 seconds after the beginning, we encounter a pivotal, theoretical concept that has gained substantial observational support: the era of cosmic inflation. This theory, first proposed by physicist Alan Guth in 1979 and further developed by Andrei Linde, Alexei Starobinsky, and others, addresses several puzzling features of our universe that would otherwise seem to require extraordinary cosmic coincidences. The cosmic microwave background radiation reveals that the early universe was remarkably uniform in temperature, with variations of only about 1 part in 100,000. This uniformity presents a mystery, because when we calculate how far light could have traveled in the time since the Big Bang, we find that regions on opposite sides of our observable universe could never have been in causal contact with each other. They are separated by more distance than light could cross in the entire age of the universe. How, then, did they achieve such precise thermal equilibrium? This is known as the horizon problem, and it challenges the standard Big Bang model. If different regions of the observable universe were never in contact, what synchronized their temperatures so perfectly? A second puzzle, called the flatness problem, concerns the geometry of our universe. Einstein's general relativity tells us that mass and energy curve space-time. With enough matter, the universe would curve back on itself, eventually recollapsing in a big crunch. With too little matter, it would curve outward, expanding ever more rapidly. Observations indicate that our universe is balanced precisely at the boundary between these possibilities, with a geometry that is flat, or very nearly so, to within 1 part in 10,000. This precise balance seems suspiciously convenient, as if the initial conditions of the universe were fine-tuned to produce exactly this outcome. Without an explanation, we are left with an apparent cosmic coincidence that demands extraordinary luck. A third mystery, called the magnetic monopole problem, arises from particle physics theories that predict the creation of exotic particles called magnetic monopoles during the extreme conditions of the early universe. These particles would have just one magnetic pole, either north or south, unlike ordinary magnets that always have both poles. Our theories suggest that magnetic monopoles should be common, yet we have never observed one. Inflation theory elegantly resolves all 3 puzzles with a single mechanism. It proposes that during a tiny fraction of the first second, our universe underwent a period of exponential expansion, stretching by a factor of at least 10 to the 26th power in less than the blink of an eye. This is not merely rapid expansion, it is expansion at an accelerating rate, doubling the size of the universe, perhaps 70 or more times in sequence. This inflationary period would have stretched a microscopic region of space, initially smaller than a proton, until it was larger than our entire observable universe today. Regions that were once close enough to establish thermal equilibrium before inflation began were catapulted far from each other, creating the illusion of regions that could never have been in contact yet somehow share the same temperature. The extreme stretching would have also flattened any initial curvature in space-time, just as the surface of a balloon appears flatter and flatter to an ant walking on it as the balloon inflates. And any magnetic monopoles that might have formed would have been diluted across such a vast volume that finding one would be like searching for a specific grain of sand in all Earth's beaches combined. But what could have powered this extraordinary period of expansion? The mathematics suggests a quantum field called the inflaton field, which existed in what physicists call a false vacuum state. This is a condition where a field appears to be at minimum energy, but this minimum is only local, like a ball resting in a small depression on a hillside, rather than at the bottom of the valley. As this field decayed to its true lowest energy state, like the ball rolling down to the valley floor, it released enormous energy that drove the exponential expansion of space. The mathematics of quantum fields allows for this kind of behavior, though the specific nature of the inflaton field remains speculative. What makes inflation theory so compelling is not just its elegant solutions to these cosmic puzzles, but the specific predictions it makes about the structure of our universe. During inflation, quantum fluctuations in the inflaton field would have been stretched from subatomic scales to cosmic scales. These fluctuations would create regions of slightly different density, the seeds for all future structure in the universe. Inflation theory predicts a specific pattern for these density fluctuations, a pattern we can observe today in the cosmic microwave background radiation. When we map the tiny temperature variations in this ancient light with sensitive instruments like the Planck satellite, we find precisely the pattern that inflation predicts, a nearly scale-invariant spectrum of fluctuations. This match between theory and observation provides strong support for inflation, though not yet definitive proof. As inflation ended, around 10 to the negative 32 seconds after the beginning, the energy of the inflaton field was converted into particles through a process called reheating. The universe was now filled with a seething soup of elementary particles, all colliding with tremendous energy in what physicists call a quark-gluon plasma. This marks the beginning of a more conventional hot Big Bang scenario, where the universe continues to expand but at a decreasing rate, cooling as it grows. From this point forward, the story becomes somewhat clearer, as our understanding of particle physics guides our reconstruction of what happened next. Between 10 to the negative 10 seconds and 10 to the negative 6 seconds after the beginning, the universe experienced a series of phase transitions as it continued to expand and cool. These phase transitions represent pivotal moments in cosmic history, when the fundamental properties of the universe changed dramatically as it crossed critical temperature thresholds. We observe phase transitions in everyday life, when water freezes into ice or boils into steam. In the early universe, these transitions were far more profound, potentially altering the very laws of physics that would govern reality forever after. One crucial transition involved the separation of the fundamental forces. According to grand unified theories, or GUTS, the strong nuclear force separated from the electroweak force, which still unified electromagnetism, and the weak nuclear force, when the universe was approximately 10 to the negative 36 seconds old. Later, when the universe was about 10 to the negative 12 seconds old, the electroweak force itself split into the electromagnetic force and the weak nuclear force. These transitions did not happen smoothly, but through a process called spontaneous symmetry breaking, analogous to how a perfectly balanced pencil standing on its tip must fall in some direction when disturbed, breaking the initial symmetry. Before these transitions, the laws of physics possessed greater symmetry, with particles and forces behaving more uniformly. After the transitions, this symmetry was broken, creating the distinct forces and particle behaviors we observe today. Another key transition occurred around 10 to the negative 11 seconds after the beginning, when the Higgs field, only recently confirmed to exist through experiments at the Large Hadron Collider, underwent its own phase transition. Before this moment, all particles were massless, traveling at the speed of light. After the Higgs field stabilized into its current state, it interacted with other particles in varying degrees, giving them the different masses we observe today. The Higgs transition is particularly significant because it fundamentally altered how matter behaves. Without mass, particles would continue to move at light speed, never slowing down to form stable structures. The universe would contain only radiation, with no possibility for atoms, molecules, or the complex chemistry necessary for life. The Higgs field, by giving mass to particles, made possible all the rich structure and diversity we see in our universe. This early period was also when matter gained a crucial advantage over antimatter. For every particle of matter, there exists a corresponding antiparticle of antimatter with identical mass but opposite charge. When particles and their antiparticles meet, they annihilate each other completely, converting their mass into pure energy. Our understanding of particle physics suggests that the early universe should have produced equal amounts of matter and antimatter, which would have annihilated completely, leaving a universe filled only with radiation. Yet clearly, matter exists. The stars, planets, and our own bodies are composed of matter, not antimatter. For reasons we still do not fully understand, the processes occurring in the superhot plasma of the early universe produce slightly more matter than antimatter, perhaps just one extra matter particle for every 10 billion matter-antimatter pairs. This tiny asymmetry, this cosmic accounting error in favor of matter, made our existence possible. Several theoretical mechanisms might explain this asymmetry, collectively known as baryogenesis. One prominent theory suggests that certain particle interactions violated what physicists call CP symmetry, treating particles and antiparticles slightly differently. Another possibility involves interactions with hypothetical very heavy particles predicted by grand unified theories. The exact mechanism remains an open question in cosmology and particle physics, a reminder that even as we reconstruct cosmic history with increasing precision, gaps in our understanding persist. By the time the universe reached 1 microsecond, or 1/1,000,000th of a second, in age, it had cooled enough for quarks to bind together, forming protons and neutrons. This process, called quark confinement, represents another phase transition. Before this point, quarks and gluons moved freely in the quark-gluon plasma. After confinement, quarks could never again exist in isolation, forever bound within composite particles. This transition is particularly interesting because it illustrates a phenomenon called asymptotic freedom, discovered by physicists David Gross, Frank Wilczek, and David Politzer, who received the Nobel Prize for this work in 2004. At extremely high energies, like those in the early universe, the strong nuclear force actually becomes weaker, allowing quarks to move freely. As the energy decreases, the force strengthens dramatically, confining quarks within protons and neutrons. We can briefly recreate these extreme conditions in particle accelerators like the Large Hadron Collider at CERN, where collisions between heavy nuclei generate temperatures hundreds of thousands of times hotter than the center of the Sun, momentarily freeing quarks from their confinement. These experiments give us glimpses into the conditions that prevailed during the first microsecond of cosmic history. Around 1 second after the beginning, the universe had expanded to roughly the size of our solar system. While still incredibly hot by everyday standards, perhaps 10 billion degrees Kelvin, it had cooled dramatically from its initial state. The cosmos was now filled with protons, neutrons, electrons, photons, and neutrinos, all interacting in a dense, energetic soup. This 1 second mark is significant for another reason. Before this time, neutrinos interacted frequently with other particles. But as the universe expanded and cooled, reaching about 10 billion degrees, these ghost-like particles decoupled from the cosmic plasma, beginning to travel freely through space, barely interacting with matter. These primordial neutrinos, created in the first, second, still permeate our universe today as a cosmic neutrino background, even older than the cosmic microwave background. Though we have not yet detected this neutrino background directly due to the extreme technical challenges involved, its existence is a firm prediction of our cosmological models. The first second of cosmic history reveals several profound insights relevant to our central question of how the universe might have created itself. First, we see that the laws of physics themselves may have emerged gradually, crystallizing from a more fundamental and symmetric state as the universe cooled. The forces and particles that govern reality today were not fixed from the beginning, but evolved through a series of phase transitions, suggesting a deeper logic or principle from which they arose. Second, the apparent fine-tuning of physical constants, the precise values that allow stable atoms and complex chemistry to exist, might be understood through the dynamics of these phase transitions. Rather than requiring an external designer to calibrate these values, they may have settled naturally into their observed states through physical processes in the early universe. Processes governed by deeper symmetries or principles we are still working to understand. Third, inflation theory suggests that our observable universe is just a tiny patch of a much larger cosmos. If the inflaton field can drive exponential expansion once, it might do so repeatedly in different regions of a vast space, creating a multiverse of bubble universes, each with its own Big Bang moment. Physicist Andre Linde developed this idea into what he calls eternal inflation, where the process of bubble universe formation continues forever without beginning or end. In such a scenario, the question of the universe's origin transforms into a question about the origin of the inflaton field and the space in which these bubble universes form. Perhaps this larger structure always existed, making our universe just one event in an eternal process. Or perhaps the multiverse itself emerged through quantum processes we are only beginning to understand. Fourth, the quantum nature of the very early universe hints at profound connections between quantum mechanics, gravity, and the nature of time itself. In quantum mechanics, particles can tunnel through energy barriers that would be insurmountable in classical physics, Could our entire universe have quantum tunneled into existence? Could what appears to us as creation ex nihilo, something from nothing, actually be a quantum transition from a pre-existing state that we cannot directly observe? The first second also reveals something about the arrow of time, the fact that time seems to flow in only one direction, from past to future. The second law of thermodynamics tells us that entropy, a measure of disorder, tends to increase over time in closed systems. The extremely low entropy of the early universe, with its remarkably uniform distribution of energy, established this arrow, creating the conditions for entropy to increase throughout cosmic history. This raises a profound question. If the early universe had such low entropy, such high order, what established these special initial conditions? Was there something before the Big Bang that set up this extraordinarily unlikely state? Or is there a deeper principle that required the universe to begin in just this way? Some theorists, including Roger Penrose with his conformal cyclic cosmology, suggest that the apparent low entropy of the early universe is connected to the fate of a previous cosmic cycle. Others, like Stephen Hawking, propose that the early universe's state might be understood through quantum cosmology, where the initial conditions are determined by a mathematical construct called the wave function of the universe. As we conclude our exploration of the first second, we are left with both greater clarity and deeper mystery. We have traced the evolution of our cosmos from an unimaginably hot, dense state through a series of phase transitions that shaped the forces, particles, and structures that would eventually lead to stars, planets, and life. We have seen how the seeds of all cosmic structure were planted in quantum fluctuations stretched to cosmic scales by inflation. Yet the ultimate questions remain. What sparked this entire process? What set the initial conditions? Was there truly a beginning? Or does our notion of time itself break down as we approach the absolute origin? To pursue these questions further, we must now examine the nature of time itself and whether it too might have emerged from the same quantum processes that gave birth to space, matter, and energy. Perhaps in understanding time's origin, we will find crucial clues to how a universe might create itself, apparently from nothing. Time flows through our lives like an invisible river, carrying us from moment to moment, from past to future. It seems so fundamental to existence that we rarely pause to question its nature. Yet time remains one of the deepest mysteries in physics and philosophy, particularly when we consider its origin. Did time itself have a beginning? Could time be circular rather than linear? Might time be an emergent property rather than a fundamental dimension? As we explore these questions, we approach the heart of how a universe might create itself. Our conventional understanding of cosmic history, supported by extensive observational evidence, tells us that our universe began in an incredibly hot, dense state about 13.8 billion years ago. As we trace this history backward toward the beginning, both space and time appear to converge to a singular point, what mathematicians call a singularity, where density and temperature become infinite and the equations of general relativity break down. This mathematical breakdown does not necessarily mean that time actually began at the Big Bang, only that our current theories cannot describe what happened at this boundary. It marks the edge of our scientific understanding, a place where our mathematical models fail and new physics must take over. But what might this new physics tell us about the nature and origin of time? Stephen Hawking, in his groundbreaking work with Roger Penrose in the 1960s and 70s, demonstrated mathematically that if general relativity is correct, and if certain reasonable conditions about the distribution of matter and energy are met, then a singularity at the beginning of the universe is unavoidable. Space and time would have begun at this singularity, with no before to speak of. In his popular book, A Brief History of Time, Hawking compared asking about what happened before the Big Bang to asking what is north of the North Pole. The question itself makes no sense, because time did not exist before the Big Bang, just as there is no north beyond the North Pole. The beginning of the universe would also be the beginning of time itself. This view challenged thousands of years of philosophical and religious thinking. Throughout history, most cultures assumed that time stretched infinitely into the past, or that the present universe was preceded by earlier creation cycles or different states of existence. The idea that time itself had a definite beginning seemed to require a creator or first cause existing outside of time, an idea expressed in cosmological arguments for God's existence, dating back to Aristotle, and elaborated by medieval philosophers like Thomas Aquinas. But modern physics suggests more complex possibilities. As we approach the Planck era, the first 10 to the negative 43 seconds after the purported beginning, quantum effects would have dominated even gravity. In this realm, the classical notion of time as a smooth, continuous dimension may lose its meaning entirely. Just as space may become discrete and granular at the Planck scale, time too might come in indivisible units, quantum moments that cannot be further subdivided. More radically, time as we experience it might be an emergent property, arising from more fundamental quantum processes, much as temperature emerges from the collective motion of molecules. In the most extreme quantum gravitational conditions near the Big Bang, this emergent quality of time becomes crucial to understanding its origin. One of the most influential approaches to this question came from Stephen Hawking's no-boundary proposal, developed with Jim Hartle in the 1980s. Using the mathematics of quantum cosmology, they proposed that asking about the beginning of time might be like asking about the edge of Earth's surface. Just as our planet's surface is finite but has no boundary or edge, time might be finite but without a beginning point. The mathematics of the no-boundary proposal is complex, involving what physicists call imaginary time, a mathematical construct where time behaves like another dimension of space. In this formulation, the early universe is represented by a smooth, rounded shape, like the surface of Earth near its south pole. As we move away from this pole, corresponding to moving forward in cosmic history, the universe expands. But there is no singularity, no edge, no absolute beginning, just as the South Pole is a completely ordinary point on Earth's surface, not a boundary or edge. If we translate this mathematical model back into our everyday notion of time, it suggests that time gradually emerged as the universe expanded and cooled, transforming from something space-like into the time dimension we experience. The absolute beginning would be smoothed away, replaced by a quantum region where time and space blur together indistinguishably. Hawking once described this by saying, "The boundary condition of the universe is that it has no boundary. The universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed, it would just be." This perspective challenges our intuitive understanding of cause and effect. We naturally ask, but what caused the universe to exist? Yet this question presupposes that time existed before the universe, allowing for a causal sequence. If time itself emerged with the universe, the concept of a cause preceding its effect becomes problematic. There would be no before in which a cause could operate. Another influential approach comes from loop quantum cosmology, an offspring of loop quantum gravity, developed by physicists including Abhay Ashtekar, Martin Bojewald, and Carlo Rovelli. In this framework, space itself has a discrete, quantum structure at the Planck scale. When these quantum principles are applied to the entire cosmos, they suggest that the singularity at the Big Bang might be replaced by a quantum bounce. In the quantum bounce scenario, the universe did not begin from a singularity, but rather contracted from a previous state until it reached a minimum size determined by quantum effects, and then began to expand again. Time would extend through this bounce, connecting our expanding universe to a previous contracting phase. While the classical equations of general relativity break down at the bounce, the quantum equations remain well behaved, allowing time to continue smoothly from before to after. This model challenges the idea that time began with our Big Bang, suggesting instead that our universe's history represents just one phase in a potentially endless cycle of contraction and expansion. Time would not have a beginning, but would stretch infinitely into the past and future, through succession after succession of cosmic cycles. Such cyclical models have deep resonances with ancient cosmologies from Hindu, Buddhist, and some Native American traditions, which envision time as circular rather than linear, with universes being created and destroyed in endless cycles. What makes the modern quantum bounce models different is that they are based on mathematical physics rather than philosophical or religious intuition, and they make specific predictions that might someday be testable through observations of the cosmic microwave background radiation or gravitational waves. A third approach to the beginning of time comes from string theory and its mathematical offspring, M-theory. In these frameworks, our universe might be a four-dimensional membrane or brain floating within a higher dimensional space called the bulk. Our Big Bang might have resulted from a collision between our brain and another, or from some other dynamic process within this higher dimensional reality. In such scenarios, time as we experience it in our four-dimensional universe might have begun with the Big Bang, but time in the higher dimensional bulk could have existed before our Big Bang and might continue after our universe ends. What we perceive as the beginning of time would be merely the beginning of time for our particular universe, not for reality as a whole. String theory also suggests the possibility of a pre-Big Bang phase, dominated by what physicists call the closed string time symmetric vacuum, a phase where the mathematics indicates time might have behaved very differently than it does in our current universe. The transition between this phase and our expanding universe could have created the illusion of a beginning of time, when in fact time continued through this transition, albeit with dramatically different properties. These diverse theoretical approaches highlights a crucial insight that the nature of time itself may be far more complex than our everyday experience suggests. What we perceive as the flow of time might be a macroscopic phenomenon, valid in our low-energy, relatively stable corner of the cosmos, but inadequate for describing the earliest moments of the universe or its ultimate nature. Quantum mechanics already challenges our intuitive understanding of time. The famous delayed choice experiments, first proposed by John Wheeler, suggest that actions in the present can influence how we must describe the past, blurring the sharp distinction between past and future. Quantum entanglement creates correlations between particles that seem to transcend normal, spatial, and temporal separation. And certain interpretations of quantum mechanics, like the many worlds interpretation, suggest that all possible futures might be equally real, branching from each quantum event into parallel realities. When we combine these quantum peculiarities with general relativity's insight that space and time form a single fabric that can stretch and bend, we begin to see how limited our everyday conception of time might be. Near black holes, for instance, time slows dramatically relative to distant observers. At the event horizon, time as experienced by an outside observer appears to stop completely. And inside the black hole, the roles of space and time effectively switch, with what was once a time dimension becoming a spatial dimension, and vice versa. If such extreme warping of space-time is possible near black holes, perhaps even more dramatic transformations of time occurred near the Big Bang, where the density and energy far exceeded anything found in black holes today. Time as we understand it might have emerged gradually from this extreme state, crystallizing into a distinct dimension only as the universe expanded and cooled. This brings us to a profound insight from modern physics, that time, rather than being an absolute framework within which events occur, might be a relational concept, defined by the interactions between different parts of the universe. Carlo Rovelli, a pioneer in loop quantum gravity, describes this perspective as relational quantum mechanics. In this view, time does not flow uniformly throughout the universe, but emerges from the web of relationships between quantum events. Different observers may experience different sequences of events, with no absolute truth about which observation is correct. What we perceive as the flow of time arises from our macroscopic perspective, averaging over countless quantum interactions to create an apparently smooth temporal progression. If time is indeed relational rather than absolute, this opens new possibilities for understanding its origin. Perhaps time did not need to be created at all, but emerged naturally from the quantum relationships that constitute reality. The question would not then be, did time have a beginning? But how did time crystallize into the form we now experience? This relational perspective on time connects to another crucial concept in understanding the origin of the universe, the nature of nothing. When we ask how the universe could have created itself from nothing, we must carefully consider what nothing means in this context. The philosophical concept of absolute nothingness, the complete absence of anything, including space, time, physical laws, or potentiality, presents a logical problem. If absolute nothing existed, there would be no structure or principle that would allow something to emerge from it. No potential, no quantum fields, no physical laws, no mechanism of any kind to initiate creation. But the nothing described by modern physics is quite different. The quantum vacuum, often described as the closest physical approximation to nothing, is actually a seething sea of virtual particles and fields, constantly fluctuating according to the principle of quantum uncertainty. Even empty space contains quantum fields with their zero-point energy. These fields obey mathematical principles and symmetries that might have existed in some form even before space and time as we know them emerged. If these quantum principles and symmetries existed in some pre-spatial, pre-temporal form, then the creation of our universe might have been less a matter of something coming from nothing and more a transition from one state of being to another, from a form of existence outside space and time to the space-time universe we inhabit. This perspective resonates with philosopher David Albert's critique of Lawrence Krauss's book, A Universe from Nothing. Albert argued that what Krauss described as nothing was actually something, a quantum vacuum governed by physical laws. The deeper question, according to Albert, is where these laws came from and why there is something, even a quantum vacuum with its laws, rather than nothing at all. But perhaps this critique rests on an outdated conception of physical laws as existing independently of the systems they describe. In modern physics, particularly in approaches to quantum gravity, the laws of physics themselves may be emergent properties rather than eternally existing truths. The symmetries and principles that govern reality might have crystallized along with space and time, not preceded them. In this view, asking what existed before the beginning of time becomes not just practically unanswerable, but conceptually problematic. If time, space, matter, energy, and even the laws of physics all emerge together from a more fundamental state, then there would be no before in the usual sense. This brings us to what may be the most radical proposal about the beginning of time, that our universe might be a self-creating system, a sort of cosmic loop. Several theoretical frameworks, including certain interpretations of quantum cosmology, suggest that the universe might create the conditions for its own existence through a causal loop that transcends our ordinary understanding of temporal sequence. Philosopher of physics Hugh Price has explored how quantum effects might allow for such retrocausal influences, where later events affect earlier ones. Cosmologist Richard Gott has proposed a model where the universe might be its own mother, creating itself through a closed time-like curve, a path through space-time that returns to its starting point. While such proposals might seem to violate causality, they become more conceivable when we recognize that the distinction between cause and effect relies on our familiar experience of time flowing in one direction. If time near the beginning of the universe behaved fundamentally differently than it does now, or if time is ultimately an emergent rather than fundamental property, then perhaps the universe could be self-causing in ways that transcend our ordinary causal reasoning. This connects to cosmological models like eternal inflation, where our universe would be just one bubble in an eternally inflating multiverse. In such models, the process of bubble universe formation continues forever, both into the future and, mathematically, into the past. There would be no first bubble, no beginning to the process, just as there is no first point when traveling clockwise around a circle. Physicist André Linde, one of the architects of eternal inflation theory, has suggested that the mathematics of inflation may even allow for the possibility that universes could create baby universes that, through the strange topology of higher dimensional space, could include their own parent universes. In such a scenario, our universe could literally be its own grandmother, existing in a causal loop that has no beginning or end. These speculative models highlight how the question of time's beginning intertwines with deeper questions about the nature of causality, the status of physical laws, and the relationship between mathematics and physical reality. Perhaps our difficulty in conceptualizing the beginning of time stems not from a lack of information, but from the limitations of human cognition, evolved as it was to navigate a macroscopic world where time flows steadily and causes precede effects. The philosopher Immanuel Kant argued in the 18th century that certain contradictions arise inevitably when human reason attempts to comprehend the absolute beginning or endless duration of the world. According to Kant, these contradictions, which he called antinomies, reveal the limits of pure reason when applied to questions that transcend possible experience. Modern physics gives new meaning to Kant's insight. If time itself is an emergent property rather than a fundamental dimension, then questions about the absolute beginning of time may be misconceived, like asking about the temperature of a single atom. a concept that only makes sense for collections of particles, not individual ones. This emergent view of time opens the possibility that our universe might be self-creating not through some paradoxical causal loop, but because time itself, and with it the very concept of creation or causation, emerged gradually from a more fundamental reality where such concepts do not apply in their familiar sense. The theoretical physicist Julian Barbour has explored this idea in depth, proposing that time does not flow but is rather a measure of the changing configuration of the universe. In his view, what we experience as the flow of time is actually the universe moving through different possible configurations, or what he calls now, each containing records of other nows that we interpret as the past. The apparent flow of time would be a psychological construct arising from comparing different configurations, not a fundamental aspect of reality. If Barbour is right, then the universe would not have created itself within time, but rather, time would be a way of organizing the relationships between different states of the universe. The beginning of time would not be a moment when something came from nothing but a boundary condition on this configuration space, perhaps the point of minimum complexity, from which complexity naturally increases. This perspective connects to the second law of thermodynamics, which states that entropy, a measure of disorder, tends to increase over time in closed systems. The arrow of time, the fact that time seems to flow in only one direction, from past to future, is intimately linked to this increase in entropy. But this raises a profound question. Why was the entropy of the early universe so extraordinarily low? What set up this special initial condition that established time's arrow? The physicist Roger Penrose has proposed that the low entropy of the early universe, which appears highly unlikely from a statistical perspective, might be explained through what he calls conformal cyclic cosmology. In this model, the far future of one universe cycle, when all matter has decayed and black holes have evaporated, leaving only massless particles in an effectively infinite space, becomes mathematically equivalent to the beginning of the next cycle. Each cycle would begin with low entropy, not because of some external intervention, but because the maximum entropy state of the previous cycle resembles a low entropy state when rescaled. Time would continue through these cycles, never beginning and never ending, but nevertheless finite in each cycle. Other approaches to the beginning of time arise from developments in quantum information theory. Some physicists, including Fotini Markopoulou and Olaf Dreyer, have proposed that space, time, and gravity might emerge from more fundamental quantum information processes. In these models, what we experience as the flow of time might correspond to the processing of quantum information, with each moment representing a computation performed on a cosmic scale. If space, time, and the laws of physics emerge from such quantum information processes, then the beginning of the universe might be reconceived as the initialization of a vast quantum computation. Time would not begin in the sense of emerging from nothing, but would represent the sequencing of this cosmic computation. The diversity of these theoretical approaches highlights an important fact about our current understanding. We do not yet have a definitive answer to whether time had a beginning, or what that beginning might have been like. The quest for a theory of quantum gravity, which would unite general relativity with quantum mechanics, continues, and such a theory might eventually provide clearer insights into the origin of time. What we can say is that multiple sophisticated mathematical frameworks suggest possibilities beyond the naive picture of time simply beginning at the Big Bang. Time might extend through a bounce from a previous contracting phase, emerge gradually from a quantum gravitational state where it was indistinguishable from space, form a closed loop with no beginning or end, or crystallize as an emergent property from more fundamental quantum processes. These possibilities do not deny the evidence for the Big Bang, but reinterpret what it means. Rather than marking the absolute beginning of everything, the Big Bang might represent a transition, boundary, or phase change within a larger reality. Time as we experience it might have begun there, but time in a broader or different sense might transcend this apparent beginning. For our central question of how the universe might have created itself, these insights about the nature of time are crucial. If time itself emerged with the universe, then the entire framework of causation, of one event causing another, may not apply to the origin of the universe. The universe would not have created itself within time, but might be a self-consistent system where time and causation emerge together. In the words of physicist John Wheeler, who pioneered many of these ideas, it may be that the universe is not only queerer than we suppose, but queerer than we can suppose. The origin of time may lie beyond our customary modes of thought, requiring new concepts that transcend our everyday understanding of before and after, cause and effect. As we continue our exploration, we will venture even deeper into quantum territory, examining how the strange properties of the quantum vacuum might allow for the spontaneous emergence of a universe. Perhaps in the quantum foam that underlies reality, we will find further clues to how a universe might create itself, not as an event in time, but as the source of time itself. We have already ventured far from everyday experience, exploring the earliest moment of cosmic history and questioning the very nature of time itself. Now we must go deeper still, into the quantum foundations of reality, where the seemingly empty vacuum teems with activity, and where entire universes might momentarily flicker into existence. This realm of quantum foam and virtual universes offers perhaps our most intriguing clues to how a universe might create itself. Our journey begins with a revolutionary insight from quantum mechanics that permanently altered our understanding of empty space. In classical physics, the vacuum was considered to be truly empty, a void containing nothing at all. But quantum mechanics reveals something far stranger. According to Heisenberg's uncertainty principle, certain pairs of properties, such as position and momentum, or energy and time, cannot both be precisely determined simultaneously. The more exactly we know one property, the less exactly we can know the other. This uncertainty principle applies even to seemingly empty space. If we could somehow measure the energy at a specific point in space for an infinitesimally brief moment, we would discover that it is not zero, but fluctuates unpredictably. Energy can appear temporarily from nothing, as long as it disappears quickly enough to maintain the average energy balance. The shorter the time interval, the larger the energy fluctuation can be. These energy fluctuations in the vacuum manifest as virtual particles, pairs of particles and antiparticles that spontaneously appear, exist briefly, and then annihilate each other, returning their borrowed energy to the vacuum. This happens continuously throughout what we call empty space, creating a quantum foam of activity at the smallest scales. This is not merely a theoretical construct. The effects of these virtual particles can be measured. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed very close together in a vacuum would experience a small attractive force. This Casimir effect, later confirmed experimentally, arises because the tiny gap between the plates restricts which virtual particles can appear in that space, creating a pressure difference between the inside and outside of the gap. Another manifestation of virtual particles appears in the energy levels of hydrogen atoms. When electrons orbit atomic nuclei, they interact with virtual particles in the vacuum, slightly altering their energy levels in ways that can be precisely measured. This effect, called the Lamb shift, after Willis Lamb, who first measured it in 1947, provides direct evidence for the reality of the quantum vacuum and its fluctuations. Perhaps most dramatically, Stephen Hawking demonstrated theoretically in 1974 that black holes can evaporate over time due to virtual particle production near their event horizons. When a particle-antiparticle pair forms near a black hole, one member of the pair might fall into the black hole while the other escapes. The escaping particle becomes real, carrying away a tiny amount of the black hole's energy, while its partner, with negative energy relative to the vacuum, reduces the black hole's mass. Over immense timescales, this Hawking radiation would cause black holes to evaporate completely. Though we have not yet directly observed Hawking radiation from astrophysical black holes, as it would be extremely faint, laboratory analogues, using sound waves in flowing fluids, have demonstrated effects mathematically equivalent to Hawking radiation, providing indirect support for the theory. These examples confirm a profound truth. What we call empty space is actually a dynamic, fluctuating system governed by the principles of quantum mechanics. The vacuum is not nothing but something, a substrate from which particles and fields can temporarily emerge. And if particles can spontaneously appear from the vacuum, albeit briefly, might not more complex structures, even universes, emerge through similar quantum processes? This question leads us to consider more extensively what happens in the quantum vacuum. According to quantum field theory, Empty space contains quantum fields, one for each type of elementary particle. These fields permeate all of space-time and can be excited to produce particles, like waves rising on an ocean. But even in their ground state, when no real particles are present, these fields contain zero-point energy, a consequence of the uncertainty principle. The quantum vacuum is thus a sea of potential, where fields exist in a state of minimum energy but can be locally excited to produce particles. This vacuum energy is not zero but has a value that, in principle, could be calculated from the quantum fields that exist in nature. This calculation, however, presents one of the greatest unsolved problems in theoretical physics. When physicists attempt to calculate the energy density of the quantum vacuum by summing the zero-point energies of all known quantum fields, they get a value that is larger than the observed value by a factor of about 10 to the power of 120. This has been called the worst theoretical prediction in the history of physics. The fact that our universe is not immediately torn apart by such an enormous energy density suggests that there must be some mechanism that almost perfectly cancels out most of this vacuum energy, leaving only the tiny residual amount we observe as dark energy. The nature of this cancellation mechanism remains one of the deepest mysteries in contemporary physics. Despite this unresolved puzzle, the concept of vacuum energy is well established in quantum field theory and provides a starting point for considering how a universe might spontaneously emerge. In 1973, physicist Edward Tryon published a paper in the journal Nature titled, "Is the Universe a Vacuum Fluctuation?" He proposed that our entire universe might have originated as a quantum fluctuation from nothing, a temporary deviation from empty space that, through a series of physical processes, evolved into the cosmos we observe today. Tryon noted that while conservation of energy would seem to forbid the spontaneous appearance of an entire universe, general relativity complicates the picture. In Einstein's theory, the total energy of a closed universe, taking into account both the positive energy of matter and radiation and the negative energy of gravitational binding, might sum to exactly zero. If the total energy is zero, then the creation of such a universe would not violate energy conservation. The physicist Frank Wilczek has expressed this idea by saying, "The universe is the ultimate free lunch. It can appear from nothing because its total energy content is zero. The positive energy of matter is balanced by the negative energy of gravity, allowing for a cosmos of vast size and complexity to arise without requiring any energy input from outside." This insight transforms our understanding of cosmic origins. Rather than requiring some external source of energy to create the universe, the very structure of general relativity, combined with quantum mechanics, might allow a universe to appear spontaneously from the vacuum. The initial quantum fluctuation would need to last only long enough for inflation to begin, after which the exponential expansion of space would prevent the universe from collapsing back into the vacuum. But could a quantum fluctuation really produce something as large and long-lasting as our universe? Here we must remember that the size of quantum fluctuations is constrained by the uncertainty principle. The larger the energy of the fluctuation, the shorter its duration must be. For a fluctuation as energetic as our entire universe, the allowed lifetime would seem to be incredibly brief, far shorter than the 13.8 billion years our universe has already existed. This apparent contradiction can be resolved by considering how time itself is affected by the extreme conditions near the beginning of the universe. In the Planck era, when quantum gravity effects would have dominated, our ordinary notion of time may not apply. What appears to us, from our current perspective, as an ancient universe that has persisted for billions of years might, from a different perspective, be a quantum event of very brief duration. Physicist Julian Barber has suggested that what we experience as the flow of time might actually be a way of organizing different configurations of the universe, different nows, each containing records of other nows that we interpret as the past. In such a perspective, the entire history of our universe might be viewed as a single quantum event, extended in what we perceive as time, but unified from a more fundamental viewpoint. Another resolution comes from considering the effects of inflation. If the initial quantum fluctuation triggered a period of inflation, the exponential expansion of space would have dramatically altered the subsequent evolution of the universe. What began as a microscopic quantum fluctuation would have been stretched to cosmic scales, and the dynamics of the inflaton field would have produced the enormous amount of matter and energy we observe today. This process would not violate energy conservation, because the positive energy of matter and radiation would be balanced by the negative energy of gravitational binding. As the universe expanded, both the positive and negative components would increase in magnitude while maintaining a sum of zero. The initial quantum fluctuation would have served as a seed, with inflation doing the work of expanding it into a vast and persistent universe. This scenario becomes even more plausible when we consider the possibility of bubble universes in eternal inflation. In this model, developed by physicists including Andrei Linde, Alan Guth, and Alexander Vilenkin, the process of cosmic inflation continues forever in some regions of space, while in other regions it ends, allowing bubble universes like ours to form. These bubble universes begin as tiny quantum fluctuations in the inflating space, nucleating like water droplets in a cloud. Each bubble expands to become a separate universe with its own physical laws, determined by how quantum fields settle into their ground states within that bubble. The process continues eternally, producing an infinite number of bubble universes in what we call the multiverse. In this picture, our universe would be just one bubble among countless others, each originating from a quantum fluctuation in the eternally inflating space. The multiverse itself might have no beginning, existing eternally in the past as well as the future. Our universe's apparent beginning, the Big Bang, would mark only the beginning of our particular bubble, not the beginning of the multiverse as a whole. But the quantum foam of space-time offers even more radical possibilities for cosmic origins. At the Planck scale, approximately 10 to the negative 35 meters, the quantum nature of space-time becomes dominant. At this scale, according to various approaches to quantum gravity, space-time itself may not be continuous but discrete, with a granular structure. Moreover, quantum fluctuations at this scale would be so energetic that they could potentially create microscopic black holes and wormholes, linking different regions of space-time. The physicist John Wheeler, who coined the term quantum foam to describe this roiling space-time, suggested that at the Planck scale, the topology of space-time might be constantly changing, with wormholes and black holes popping in and out of existence. These topological fluctuations would give space-time a complex, foam-like structure at the smallest scales, far from the smooth continuum we experience at macroscopic scales. This quantum foam might serve as the foundation for universe creation. Some theoretical approaches to quantum gravity, including certain formulations of string theory and loop quantum gravity, suggest that microscopic black holes could serve as seeds for new universes. When a quantum fluctuation produces a microscopic black hole, the interior of this black hole might inflate to form a new region of space-time, essentially a baby universe connected to its parent universe by an extremely short-lived wormhole. Physicist Lee Smolin has developed this idea into a theory of cosmic natural selection, proposing that black holes might give birth to new universes with slightly varied physical laws. If universes that produce more black holes have more cosmic offspring, then over many generations of universe creation, the multiverse would become dominated by universes whose physical laws maximize black hole production. Interestingly, such universes would also tend to allow for the existence of stars and potentially life, as the same conditions that favor black hole formation also favor star formation. This scenario suggests not only how universes might be created from quantum fluctuations, but also why our universe has the particular physical laws it does. Rather than requiring a designer to fine-tune the constants of nature, cosmic natural selection could explain the apparent fine-tuning as the result of an evolutionary process operating at the level of universes. Another intriguing possibility arises from considering virtual particles in the quantum vacuum. Virtual particles are not constrained by the same rules as real particles. They can travel faster than light, move backward in time, and violate energy conservation temporarily. In certain interpretations of quantum mechanics, particularly the transactional interpretation developed by John Cramer, quantum events involve a handshake between retarded waves moving forward in time and advanced waves moving backward in time. This bidirectional causality at the quantum level hints at how a universe might bootstrap itself into existence. If quantum processes can involve influences propagating both forward and backward in time, perhaps the universe as a whole exists within a giant quantum transaction, a self-consistent loop where later states influence earlier ones through quantum retrocausality. Physicist Richard Feynman's path integral formulation of quantum mechanics provides a mathematical framework for considering such possibilities. In this approach, quantum particles do not follow a single path through spacetime, but explore all possible paths simultaneously, with the observed behavior emerging from the sum over all these possibilities. Applied to the universe as a whole, this suggests that the cosmos might sample all possible histories, with our observed universe representing the most probable history, a kind of quantum average over all possibilities. In such a framework, the beginning of the universe need not be a singular event causally disconnected from what follows. Instead, the entire cosmic history would form an interconnected whole, with later states constraining earlier ones through the mathematical structure of the quantum path integral. The universe would select its own initial conditions to be compatible with its later evolution, creating a self-consistent loop that has no beginning in the conventional sense. These ideas remain speculative, at the frontier of theoretical physics, yet they illustrate how the quantum nature of reality might allow for forms of self-creation that transcend our everyday understanding of causality. In the quantum realm, effects can precede causes, systems can exist in superpositions of different states, and the act of observation can retroactively determine what must have happened in the past. Applied to the universe as a whole, these quantum principles open possibilities for cosmic self-creation that would be inconceivable in classical physics. The quantum vacuum offers one more pathway to consider for universe creation, the concept of vacuum decay or false vacuum collapse. According to quantum field theory, quantum fields can exist in different energy states, including what are called false vacua, states that appear stable but are actually higher in energy than the true vacuum state. A field in a false vacuum state might remain there indefinitely, unable to reach its true lowest energy state because of an energy barrier, much like a ball in a small depression on a hillside cannot roll down to the valley floor without first being pushed over the surrounding ridge. However, quantum tunneling allows for the possibility that a region of space in a false vacuum state could spontaneously transition to the true vacuum state, bypassing the energy barrier through quantum processes. This transition would release enormous energy and could potentially trigger an expanding bubble of true vacuum that would grow at nearly the speed of light, eventually converting the entire false vacuum to the true vacuum state. Cosmologists have speculated that our universe might have begun as just such a vacuum decay event in a pre-existing space dominated by an inflaton field in a false vacuum state. A tiny region of this space quantum tunneled to a lower energy state, releasing energy that drove the expansion of our universe. The bubble of true vacuum would expand, creating a new universe with different physical properties than the original false vacuum. More dramatically, some physicists have suggested that our current vacuum state might itself be a false vacuum, metastable rather than truly stable. If this is the case, our universe might someday experience a vacuum decay event, with a bubble of true vacuum nucleating somewhere and expanding to convert our entire observable universe to this new state, with potentially different physical laws and constants. While this possibility might sound alarming, if it does happen, the bubble would expand at nearly the speed of light, giving us no warning and no possibility of escape. The false vacuum scenario offers yet another mechanism by which quantum processes could lead to the creation of a universe. Rather than requiring the universe to emerge from absolute nothing, this model suggests it could arise from the decay of a pre-existing state through quantum tunneling. The energy released in this decay would provide the seed for all the matter and radiation in our universe, while the expansion would create all of space as we know it. These diverse quantum mechanisms for universe creation, from vacuum fluctuations to black hole bounces to vacuum decay, share a common theme. They all suggest that the fundamental randomness and uncertainty inherent in quantum mechanics might allow for the spontaneous emergence of complex, ordered systems from simpler states. The quantum vacuum, far from being truly empty, contains the seeds of countless potential realities, occasionally giving rise to bubble universes like our own. This perspective transforms our understanding of cosmic origins. Rather than requiring a precise sequence of highly unlikely events to produce our universe, quantum mechanics suggests that universe creation might be a natural, even inevitable process, occurring repeatedly throughout an eternally inflating multiverse. Our universe would not be a singular miracle, but one instance of a universal phenomenon, the quantum birth of cosmos from the void. Yet even this rich quantum picture leaves deeper questions unanswered. Where did the quantum vacuum itself come from? Why do quantum fields exist at all? Why does quantum mechanics work the way it does? The quantum origin of our universe might explain how it emerged from a pre-existing quantum state, but it does not fully address the ultimate question of why there is something rather than nothing. Here we reach the boundary between physics and philosophy, between what we can investigate scientifically and what may lie beyond the reach of empirical inquiry. Some physicists, like Stephen Hawking, have suggested that the ultimate laws of physics, the mathematical structures that govern quantum mechanics and gravity, might exist necessarily, independent of any physical realization. In this view, the laws themselves would not need a cause or explanation, as they would exist as mathematical truths rather than physical objects. If the fundamental laws of physics include quantum mechanics with its inherent uncertainties and fluctuations, then perhaps the emergence of universes is a logical necessity, as inevitable as the existence of the mathematical principles themselves. The quantum vacuum, with its virtual particles and fluctuating fields, would be a physical manifestation of these necessary mathematical structures. Others, like cosmologist Sean Carroll, have proposed that the multiverse simply exists as a brute fact, without requiring further explanation. In this perspective, the question, why is there something rather than nothing, may have no answer beyond. The multiverse exists because it exists. The stream of cause and effect would operate within the multiverse, but would not apply to the multiverse as a whole. Still others, including physicist Leonard Susskind, have suggested that the multiverse may be the only logically consistent possibility. If all mathematically possible universes exist, then there would be no need to explain why one particular universe, or type of universe, exists rather than another. This perspective, sometimes called the mathematical universe hypothesis, proposes that reality at its deepest level is a mathematical structure, with our physical universe being one manifestation of this abstract mathematics. These philosophical perspectives on the ultimate origin of the quantum vacuum and the laws of physics remind us that some questions may lie beyond the reach of scientific inquiry, at least as we currently understand it. Yet the remarkable progress of physics in explaining how quantum processes could lead to the birth of universes suggests that we should not be too quick to declare any question permanently unanswerable. The study of quantum foam and virtual universes reveals a picture of the cosmos far stranger and more wonderful than our ancestors could have imagined. The apparently empty void teems with activity at the quantum scale. As particles and antiparticles flicker in and out of existence, energy fluctuates according to the uncertainty principle, and the very fabric of space-time roils with topological changes. From this quantum foam, entire universes might bubble up naturally, expanding to produce vast regions of space-time with their own physical laws and structures. In this picture, our universe would not require a creator or first cause external to itself. It would emerge through natural quantum processes, as one bubble in an eternally frothing sea of creation. The apparent fine-tuning of physical constants might be explained through cosmic natural selection or the anthropic principle, which we will explore in later chapters. And the deep mathematical structure of reality, particularly the interplay between quantum mechanics and gravity, might contain within itself the seeds of its own existence. As we venture further in our exploration, we will examine how these quantum insights connect to the broader question of creation from nothing. We will consider how quantum processes might allow for the emergence of a universe with zero total energy, how the multiverse might encompass all logically possible physical laws, and how consciousness itself might play a role in the quantum creation of reality. But first, let us delve deeper into the concept of nothingness itself, and how modern physics transforms our understanding of what it means for something to come from nothing. Nothing, the absence of everything, the void. Throughout human history, the concept of absolute nothingness has both fascinated and troubled philosophers, theologians, and scientists. Aristotle famously declared that nature abhors a vacuum, suggesting that true emptiness could not exist. Medieval philosophers debated whether God could create a perfect vacuum, and in modern times, the question of how something, particularly an entire universe, could emerge from nothing has driven some of our most profound scientific and philosophical inquiries. In this chapter, we explore how modern physics has transformed our understanding of nothingness itself, and how this transformed understanding might resolve the ancient puzzle of creation ex nihilo, something from nothing. We will see how the conservation of energy, one of physics' most sacred principles, might actually allow for the spontaneous emergence of an entire cosmos. And we will confront the possibility that the apparent contradiction of creation from nothing dissolves when we precisely define what we mean by nothing. Our exploration begins with physicist Lawrence Krauss, whose 2011 book, A Universe from Nothing, popularized the idea that modern physics can explain how a universe might emerge from nothing without violating any physical laws. Krauss argues that the traditional philosophical puzzle assumes an outdated conception of nothingness, one that modern quantum physics has rendered obsolete. According to Krauss, even the most perfect vacuum, completely devoid of particles and radiation, still contains quantum fields in their ground states. These fields, constrained by the uncertainty principle, fluctuate continuously, briefly producing virtual particles that appear and disappear. What might appear to be nothing actually contains the seeds of everything, an inherent creative potential embedded in the very structure of quantum reality. Moreover, when we consider the total energy of the universe, taking into account both the positive energy of matter and radiation and the negative energy of gravitational binding, the sum might be exactly zero. As physicist Frank Wilczek has noted, this would make the universe the ultimate free lunch, requiring no net input of energy for its creation. The matter and energy we observe would be balanced precisely by the negative gravitational energy of space, allowing a universe of vast complexity to emerge from nothing with no violation of energy conservation. The mathematics of this balance is deeply connected to the geometry of the universe. In general relativity, the curvature of space-time is determined by the distribution of matter and energy. A universe with a perfectly flat geometry, which observations suggest our universe closely approximates, would have exactly zero total energy. This perfect balance between positive and negative energy components would allow the universe to emerge from nothing through a quantum fluctuation, without requiring any external input or violating energy conservation. This perspective transforms our understanding of cosmic origins. Rather than requiring some external cause or creator to inject energy into nothingness, producing the universe, the very structure of physical law might allow a universe to appear spontaneously, its vast positive energy content perfectly balanced by its negative gravitational energy. But this explanation has not satisfied all philosophers and scientists. Some critics, including philosopher David Albert, have argued that what Krauss describes as nothing is actually something, a quantum vacuum governed by physical laws. The quantum fields that fluctuate in empty space, producing virtual particles, still represent a kind of existence. The laws of physics that allow these fluctuations still represent a kind of order. True nothingness, the complete absence of anything, would include the absence of quantum fields and physical laws as well. This critique highlights a crucial point about the concept of nothing. When we ask how something can come from nothing, we must specify precisely what we mean by nothing. Do we mean a perfect vacuum within existing space, devoid of particles but still containing quantum fields? Do we mean the absence of space and time themselves? Do we mean the absence of physical laws and mathematical relationships? Each definition leads to different understandings of cosmic origins. Krauss acknowledges this conceptual challenge, but argues that the definition of nothing has evolved as our scientific understanding has progressed. Just as we once thought empty space was truly empty, before discovering fields and virtual particles, perhaps what we now consider to be nothing, the absence of space and time, might itself contain deeper structures that can give rise to universes. The nothing of today might be revealed as something by the science of tomorrow. This perspective resonates with recent developments in quantum gravity, where space-time itself is understood as an emergent property arising from more fundamental quantum processes. In approaches like loop, quantum gravity, and causal set theory, space and time are not fundamental, but emerge from networks of quantum relationships. What seems like nothing, the absence of space and time, might actually be a more fundamental quantum reality from which space and time crystallize under certain conditions. These insights have led some theorists to propose that the absence of space and time what we might consider absolute nothingness, could itself be unstable. Just as a perfect vacuum is unstable against quantum fluctuations that produce virtual particles, perhaps the absence of space and time is unstable against fluctuations that produce entire space-time regions, bubble universes that expand from nothing through natural quantum processes. The physicist Alexander Vilenkin has developed mathematical models showing how a universe might quantum tunnel into existence from nothing, defined as the absence of space, time, matter, and energy. In his approach, the laws of quantum mechanics would operate even in the absence of space-time, allowing for a quantum transition from no space-time to an infinitesimal, embryonic space-time that could then inflate to cosmic scales. This scenario does not require a pre-existing space within which the universe appears. Rather, space itself is created in the quantum tunneling event, expanding from a point of essentially zero size. Time begins with this tunneling event, with no before in the conventional sense. The universe would truly come from nothing, at least nothing spatial or temporal, through purely quantum processes. But even this sophisticated model leaves a deeper question: where do the laws of quantum mechanics come from? If quantum mechanics allows universes to pop into existence from nothing, what established quantum mechanics itself? Are the laws of physics themselves emergent, or do they exist in some sense independent of physical reality? Some theorists have proposed that the fundamental laws of physics, particularly the mathematical structures that underlie quantum mechanics and relativity, might exist necessarily as mathematical truths rather than physical objects. In this view, championed by physicists like Max Tegmark, reality at its deepest level is mathematical in nature. What we experience as physical reality would be one expression of this deeper mathematical reality. If the fundamental laws of physics include quantum mechanics with its uncertainties and fluctuations, and if these laws exist necessarily as mathematical truths, then perhaps the emergence of universes is a logical necessity, following inevitably from the mathematical structure of reality. The question would not be, how did something come from nothing? But how could nothing have remained nothing, given the inherent creative potential in the mathematical structures that govern reality? Another perspective comes from information theory and computation. Some approaches to quantum gravity, including proposals by physicists like Seth Lloyd and Fotini Markopoulou, suggest that reality at its most fundamental level consists of information and computation. Space, time, and physical objects would emerge from networks of quantum information processing, much as the three-dimensional world we experience in virtual reality emerges from computational processes in computer hardware. In such models, what we call nothing might correspond to a state of minimal or unstructured information, while something, including space, time, and matter, would correspond to organized information patterns. The emergence of a universe from nothing would represent a spontaneous increase in the complexity and organization of information, a natural process that might be inevitable given the underlying dynamics of quantum information. These diverse perspectives on nothingness and the emergence of something from nothing share a common theme. They all suggest that true nothingness, the complete absence of everything, might be logically or physically impossible. There may always be something, whether quantum fields, mathematical structures, or information, from which physical reality can emerge through natural processes. This insight transforms the traditional question: why is there something rather than nothing? Perhaps there cannot be nothing in the absolute sense. Perhaps what we think of as nothing always contains the potential for something, and this inherent creative potential is itself necessary and eternal. The physicist John Wheeler expressed a related idea through his concept of it from bit, suggesting that the physical universe emerges from information. Every it, every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from binary choices, bits. Information may be more fundamental than physical reality, existing necessarily rather than contingently. These perspectives on nothing and its creative potential connect to ancient philosophical traditions. Taoism speaks of the Tao as an infinite potential from which all things emerge, while remaining itself formless and indescribable. Buddhist philosophy identifies sunyata, emptiness, not as a nihilistic void, but as the fertile ground of infinite possibility. And in Western philosophy, Heidegger contrasted das Nichts, the nothing, with beings or things, suggesting that the nothing is not the negation of beings, but the source from which being itself emerges. Modern physics gives new meaning to these philosophical insights, providing mathematical frameworks that describe how universes might emerge from states of minimal structure through natural processes. What was once the realm of mystics and metaphysicians has become the domain of equations and experiments, as science probes the boundary between being and non-being. This scientific approach to nothingness and creation takes on particular significance when we consider the role of energy in cosmic origins. Energy, the capacity to do work, takes many forms in our universe, from the kinetic energy of moving objects to the potential energy of gravitational fields, from the electromagnetic energy of light to the nuclear energy bound within atoms. In classical physics, one of the most fundamental principles is the conservation of energy, the idea that energy can be transformed from one form to another, but never created or destroyed. At first glance, this principle seems to forbid the spontaneous creation of an entire universe, with its vast energy content, from nothing. Creating all the matter, radiation, and other forms of energy in our universe would appear to require an enormous input of energy from somewhere, violating conservation if this energy came from nowhere. Yet here we encounter one of the most profound insights of modern physics. In general relativity, gravitational energy is negative. When objects are bound together by gravity, they have less energy than the same objects would have if separated by infinite distances. This negative gravitational energy exactly balances the positive energy of matter and radiation in a universe with a flat geometry, making the total energy zero. The mathematician Stephen Hawking expressed this idea clearly. Every body in the universe attracts every other body with a force, which is proportional to the product of their masses and inversely proportional to the square of the distance between them. This means that when I hold a kilogram of matter in my hand, I feel the Earth pulling it down with a gravitational force, but the kilogram also pulls the Earth up toward it with an equal force. If the total energy of the universe must be zero, and it costs positive energy to create matter, then this energy must be balanced by negative energy elsewhere. The obvious place for this negative energy is gravity. Hawking went on to explain, because gravity is attractive, gravitational energy is negative. One can think of the positive energy of matter as being balanced by the negative energy of the gravitational field. So the energy of the universe is zero, but it may be divided into a positive part, which is matter, and a negative part, which is the gravitational field. This zero-energy universe concept transforms our understanding of cosmic origins. A universe with zero total energy could emerge from nothing without violating energy conservation. The vast positive energy of all matter and radiation would be exactly balanced by the negative energy of the gravitational field, allowing the creation of everything we observe without requiring any input from outside the universe itself. The mathematics of general relativity shows that a universe with a flat geometry, which observations suggest our universe closely approximates, would have exactly zero total energy. The precision of this balance is remarkable. If the total energy were even slightly positive, the universe would expand forever, thinning out until no structures could form. If it were slightly negative, the universe would recollapse before stars and planets could form. The fact that the energy balance appears to be exactly zero, corresponding to a flat geometry, suggests a profound underlying principle at work in cosmic origins. This zero-energy balance allows us to reconceptualize the origin of the universe. Rather than requiring energy to be injected from outside, creating the cosmos, the origin would involve a redistribution of energy, with positive and negative components separating and balancing each other. The total would remain zero, in perfect accord with conservation principles, while allowing for the emergence of a vast and complex universe. This perspective connects to the quantum fluctuations we explored earlier. In quantum mechanics, the uncertainty principle allows energy to fluctuate, with particles and antiparticles briefly appearing from the vacuum. The amplitude of these fluctuations is limited by the uncertainty principle, with larger energy fluctuations allowed only for shorter durations. For a quantum fluctuation to produce an entire universe, it would seem to require an enormous energy fluctuation, far beyond what the uncertainty principle would normally allow given the age of our universe. But the zero-energy balance resolves this problem. If the total energy of the universe is exactly zero, then creating it would not require any net energy fluctuation at all. The positive and negative components could separate through a quantum process, initiating the expansion of space without violating the uncertainty principle. This separation of positive and negative energy components connects to the concept of symmetry breaking in physics. Initially, the universe may have existed in a highly symmetric state, with energy distributed uniformly. As it expanded and cooled, this symmetry would break, with energy separating into the positive energy of matter and radiation and the negative energy of the gravitational field. The total would remain zero, but the distribution would become increasingly complex, allowing for the formation of galaxies, stars, planets, and eventually life. The physicist Edward Tryon, who first proposed the universe as a vacuum fluctuation in 1973, expressed this idea by saying, "The universe is simply one of those things that happens from time to time. If the total energy is zero, then the spontaneous emergence of a universe would be no more mysterious than the temporary appearance of virtual particles in the quantum vacuum, just occurring on a grander scale." This quantum perspective on cosmic origins suggests a universe that is fundamentally self-creating and self-sufficient. Rather than requiring an external cause or creator, the universe might emerge naturally from nothing through processes inherent in the very fabric of reality. The question, "What created the universe?" becomes less about finding some prior entity or event, and more about understanding the intrinsic creative potential in nothingness itself. But even this sophisticated scientific account leaves deeper questions unanswered. If quantum mechanics allows universes to emerge from nothing, where did quantum mechanics itself come from? If the laws of physics permit or even necessitate creation from nothing, what established these laws? These questions push us to consider the status of physical laws themselves. Are they external to the universe, existing independently of physical reality, or are they emergent, arising along with the universe itself? Some theorists have proposed that the laws of physics themselves evolved during the earliest moments of the universe. In the extreme conditions near the Big Bang, what we now recognize as fundamental laws may have been in an undifferentiated state, crystallizing into their current form as the universe expanded and cooled. Rather than being eternally fixed, the laws of physics might have emerged gradually through a process analogous to the phase transitions that turned the early plasma of fundamental particles into the structured cosmos we observe today. This perspective suggests a deeper kind of self-creation, where not only the contents of the universe, but its fundamental laws emerge together through a self-organizing process. The universe would not simply comply with pre-existing laws, but would generate its own rules as it developed, a kind of cosmic evolution operating at the most fundamental level. Others, like physicist Max Tegmark, have proposed the mathematical universe hypothesis, suggesting that physical reality is a mathematical structure. All possible mathematical structures would exist in some sense, with our particular universe corresponding to one such structure. The laws of physics would not be separate from the universe, but would be the mathematical relationships inherent in the structure that constitutes our reality. In this view, the emergence of a universe from nothing would represent the realization of one mathematical possibility from a vast landscape of potential realities. The nothing from which our universe emerged would not be an absolute void, but the abstract realm of mathematical possibility, which exists necessarily rather than contingently. These perspectives challenge our conventional understanding of causality and existence. We typically think of causes preceding their effects in time, with one event leading to another in a temporal sequence. But if time itself emerged with the universe, then the origin of the cosmos cannot fit into this conventional causal framework. The universe would not be caused by something before it, because there was no before. Instead, its existence might be self-explaining, arising from principles or structures that exist necessarily rather than contingently. The philosopher Gottfried Wilhelm Leibniz addressed a similar question in the 17th century with his principle of sufficient reason, which states that everything must have a reason or cause. When applied to the universe as a whole, this principle leads to what Leibniz called the ultimate question: why is there something rather than nothing? Leibniz concluded that the answer must lie in a necessary being, God, whose existence is self-explaining. Modern physics suggests alternative possibilities. Perhaps the fundamental laws of nature, or the mathematical structures that underlie them, exist necessarily in the way that mathematical truths exist necessarily. The equation 2 + 2 = 4 is not contingent but necessary, true by its very nature. If the laws of physics have a similar, necessary existence, and if these laws include quantum mechanics with its creative fluctuations, then the emergence of universes might itself be necessary rather than contingent. Another perspective comes from considering probability in an infinite context. If all possible universe configurations have some probability of occurring through quantum processes, and if we consider an infinite time or an infinite multiverse, then all possibilities with non-zero probability would eventually be realized. Our universe would exist simply because it can exist. Its probability is not zero, and in an infinite context, everything possible eventually happens. The cosmologist Sean Carroll has argued that the multiverse itself might be the ultimate brute fact, existing eternally without requiring further explanation. Within the multiverse, cause and effect would operate normally, but the multiverse as a whole would not be caused by anything outside itself. It would simply exist. In this view, asking why there is something rather than nothing might be like asking why mathematical truths are true. They simply are, by their very nature. These perspectives suggest that the traditional concept of creation, with a creator acting to produce something from nothing, might be based on an outdated framework. If the universe is self-creating through quantum processes, if its laws emerged along with its contents, if its total energy is exactly zero, making its appearance consistent with conservation principles, then the need for an external creator largely dissolves. This does not necessarily conflict with religious or spiritual perspectives, which might reinterpret divine creation in light of these scientific insights. Perhaps what some traditions call God is not an external being who created the universe from outside, but the creative potential inherent in nothingness itself, the mathematical structures or quantum processes from which reality emerges. The theologian Paul Tillich spoke of God as the ground of being rather than as a being among beings, a perspective that resonates with the scientific understanding of cosmic origins emerging from contemporary physics. As we conclude our exploration of the universe from nothing, we recognize that modern physics has transformed our understanding of both nothingness and creation. What once seemed an insurmountable logical problem, how something could come from nothing, appears increasingly addressable within a scientific framework. The apparent contradiction dissolves when we precisely define what we mean by nothing and when we recognize the creative potential inherent in quantum reality. The universe from nothing represents perhaps the most profound example of emergence in nature, where complex structures and behaviors arise from simpler foundations through natural processes. Just as life emerges from non-living matter through biological evolution, just as consciousness emerges from neural activity through the complexity of the brain, the entire cosmos may have emerged from quantum nothingness through processes inherent in the mathematical structure of reality. This perspective does not eliminate mystery but transforms it. The wonder is not that something impossible occurred, requiring supernatural intervention, but that the fabric of reality itself contains the potential for its own creation and evolution. The universe may be self-creating, self-organizing, and self-explaining, a manifestation of the creative potential inherent in the quantum vacuum, the mathematical structures underlying reality, or the information patterns from which physical existence emerges. As we move forward in our exploration, we will consider how this perspective on cosmic origins connects to the apparent fine-tuning of physical constants, the emergence of complexity in life, and the possibility that our universe is one of many in a vast multiverse. We will examine how the self-creating universe might select its own laws, giving rise to conditions that allow for the emergence of conscious observers who can contemplate their own origins. And we will consider how the observer effect in quantum mechanics might suggest a deeper role for consciousness in the creation and evolution of reality. The universe from nothing represents not the end of our inquiry, but a new beginning, a framework for understanding cosmic origins that integrates the latest scientific insights while acknowledging the profound philosophical questions that remain. As we continue to explore, we may find that the universe is not only stranger than we imagine, but stranger than we can imagine, a reality whose ultimate nature may transcend the categories of our thought, while remaining accessible to our mathematical description and scientific investigation. Throughout human history, our conception of the cosmos has repeatedly expanded. From a flat Earth at the center of a small universe, we gradually discovered that we live on one planet among many, orbiting an ordinary star, in one galaxy among billions, in an observable universe, stretching billions of light years in all directions. Each expansion of our cosmic perspective has diminished our apparent centrality while revealing a reality more vast and wondrous than previously imagined. Now we stand at the threshold of perhaps the greatest expansion of our cosmic perspective yet, the possibility that our entire observable universe, with its billions of galaxies stretching across billions of light years, might be just one universe among countless others in a vast multiverse. This concept, once purely speculative, has emerged from multiple strands of contemporary physics, from inflation theory to string theory to quantum mechanics, suggesting that the multiverse may be not merely possible but perhaps even necessary given our current understanding of physical law. The implications of a multiverse for our question of cosmic self-creation are profound. If our universe is one of many, each with potentially different properties and physical laws, this might explain why our particular universe appears so exquisitely tuned for complexity and life. It might reveal mechanisms by which universes can reproduce or evolve. And it might suggest that the creation of our universe was not a singular, unique event, but one instance of a natural, ongoing process occurring throughout the multiverse. Our exploration begins with cosmic inflation, the theory that our universe underwent a period of exponential expansion during its earliest moments. As we discussed in earlier chapters, inflation elegantly explains several puzzling features of our cosmos, including its remarkable uniformity, flat geometry, and lack of magnetic monopoles. The inflationary model has received strong observational support, particularly from detailed measurements of the cosmic microwave background radiation. But the mathematics of inflation, developed by physicists like Alan Guth, Andrei Linde, and others, suggests that inflation might not be a one-time event that happened only at the beginning of our universe. Instead, inflation might be eternal, continuing forever in some regions of space while ending in others, creating a multiverse of bubble universes, each with its own distinctive properties. To understand how this eternal inflation would work, we must consider the quantum nature of the inflaton field, the field that drives cosmic expansion. Like all quantum fields, the inflaton field experiences random fluctuations. In regions where these fluctuations cause the field to decay to a lower energy state, inflation ends, allowing a hot Big Bang universe like ours to form. But in other regions, quantum fluctuations might push the field back up to higher energy states, causing inflation to continue. When we analyze the mathematics, we find that once inflation begins, the volume of space undergoing inflation grows exponentially, faster than the volume transitioning to non-inflationary states. Even as bubble universes continuously form, the inflating space between them expands even more rapidly, creating room for ever more bubbles to form. The process has no end and, mathematically, no beginning either. Inflation would be truly eternal, with our universe representing just one bubble in an eternally frothing sea of creation. Physicist Andrei Linde, one of the architects of eternal inflation theory, describes this process using the metaphor of a cosmic fractal, similar to how we see in certain mathematical patterns that repeat at different scales. If you could somehow view the multiverse from outside, you would see a self-similar structure, with bubble universes nested within still inflating regions, which themselves contain more bubble universes, and so on, without end. Each of these bubble universes would begin with its own Big Bang, as the energy of the inflaton field converts into a hot plasma of particles. Each would expand and cool according to its own cosmic parameters. And crucially, each might have different physical properties, different values for the constants of nature, and even different physical laws. This variation arises because the inflaton field and other quantum fields must settle into their lowest energy states, or vacua, as each bubble universe forms. Quantum theory suggests that these fields might have multiple possible vacuum states, each corresponding to different physical properties. The particular vacuum state selected in each bubble universe would be determined by quantum processes, introducing an element of randomness into which physical laws and constants manifest in each universe. This quantum landscape of possible vacuum states connects eternal inflation to another theoretical framework that independently suggests a multiverse: string theory. String theory attempts to unify all fundamental forces, including gravity, by proposing that the basic constituents of reality are not point particles, but tiny one-dimensional strings, whose different vibration patterns correspond to different particles. The mathematics of string theory requires additional spatial dimensions beyond the three we directly experience. These extra dimensions would be curled up or compactified to such small scales that we do not notice them in everyday life. Crucially, these extra dimensions can be compactified in an enormous number of different ways, perhaps 10 to the 500 different configurations, each leading to different physical laws and constants in the resulting four-dimensional space-time. If string theory is correct, and if eternal inflation provides a mechanism for sampling these different possible configurations, then the multiverse would contain an almost unimaginable diversity of bubble universes, each with its own physical laws. Some would collapse immediately, others would expand forever, becoming cold and diffuse, and a select few might have just the right properties to allow for the formation of stars, planets, and potentially life. This vast landscape of possible universes transforms our understanding of cosmic fine-tuning. Observations indicate that many physical constants in our universe appear exquisitely calibrated to allow for complexity and life. If even one of several key constants were slightly different, stars could not form, chemistry would not work, or structures would not emerge. This apparent fine-tuning has been cited as evidence for design or purpose in the cosmos. But in a multiverse containing universes with all possible physical properties, some universes would, by chance alone, have constants within the narrow ranges that permit complexity and life. Conscious observers like ourselves could only arise in those universes with the right properties, so we should not be surprised to find ourselves in a universe that appears fine-tuned for our existence. This reasoning, known as the anthropic principle, suggests that the apparent fine-tuning of our universe might be a selection effect rather than evidence of design. The string theory landscape combined with eternal inflation offers one version of the multiverse, but other theoretical frameworks suggest additional types. Physicist Max Tegmark has categorized these into 4 levels, each representing a more radical expansion of our cosmic perspective. Level 1, the most conservative, suggests that space extends infinitely beyond our observable horizon, containing regions identical to our observable universe, along with every possible variation consistent with the same physical laws and constants. This infinite space would contain infinite copies of each possible configuration of matter, including copies of Earth and even ourselves, simply because in an infinite space, every possible arrangement of particles must repeat infinitely. Level 2 corresponds to the bubble universes of eternal inflation, where different regions might have different physical laws and constants. This level includes the string theory landscape we have discussed, where each bubble universe samples different possible compactifications of the extra dimensions. Level 3 arises from the many worlds interpretation of quantum mechanics, which proposes that all possible outcomes of quantum measurements occur, with reality branching into parallel worlds. In this view, the wave function of the universe never collapses into a single outcome, but continues to encompass all possibilities, with our consciousness following just one branch of an ever-splitting reality. If correct, this would imply an even greater multiplication of realities, with the universe branching into parallel versions at every quantum event. Finally, Level 4, the most speculative, suggests that all mathematically possible universes exist, not just those consistent with our particular mathematical structures like quantum mechanics and general relativity. Any universe that can be described by a consistent mathematical structure would exist in the same sense that our universe exists, creating a multiverse that encompasses all logically possible realities. These different levels of the multiverse are not mutually exclusive. Our reality might include all 4 types simultaneously, with infinite space containing bubble universes with different laws, each splitting into quantum branches, all embedded within the landscape of all mathematical possibilities. The multiverse concept has profound implications for cosmic self-creation. Rather than requiring a singular act of creation that produced our universe from nothing, it suggests an eternal process of universe formation occurring naturally throughout the multiverse. Our universe would not be unique or privileged, but one instance of a universal phenomenon, the quantum birth of cosmos from vacuum. This perspective resonates with the philosophical principle known as the principle of sufficient reason, articulated by Gottfried Wilhelm Leibniz, which holds that everything must have a reason or cause for why it is as it is rather than otherwise. Applied to the entirety of existence, this principle leads to the question, why is there something rather than nothing? And why this particular reality rather than another? The multiverse offers a potential resolution to these questions. If all possibilities exist somewhere in the multiverse, then there would be no need to explain why one particular reality exists rather than another. All realities would exist, with our experience confined to the particular bubble universe compatible with our existence. The question would not be, why this reality, but why do we experience this particular reality? The anthropic principle provides the answer. We experience this reality because it is one of the relatively rare regions of the multiverse where conscious observers can exist. As for the deeper question, why is there something rather than nothing? The multiverse suggests that perhaps this distinction is not as clear-cut as it appears. If the total energy of each universe sums to zero, as discussed in our previous chapter, then the creation of everything we observe requires no net energy. If quantum fluctuations occur naturally and necessarily, as inherent features of reality, then the emergence of universes might be inevitable rather than contingent. And if all mathematically possible structures exist in some sense, as level 4 of the multiverse suggests, then existence itself might be necessary rather than contingent, leaving no room for absolute nothingness. The multiverse concept has faced criticism from some scientists and philosophers. Critics argue that if other universes are by definition beyond our observable horizon, they cannot be directly observed or tested, placing the multiverse outside the realm of empirical science. Some suggest that the multiverse represents a retreat from the traditional scientific goal of finding specific explanations for specific phenomena, replacing it with a statistical approach that explains observations through selection effects from an ensemble of possibilities. Proponents respond that while other universes might not be directly observable, the multiverse hypothesis itself can be tested indirectly. If our universe is one of many bubble universes formed through eternal inflation, this might leave detectable signatures in the cosmic microwave background radiation, particularly in the pattern of temperature fluctuations at the largest scales. Similarly, if our universe collided with another bubble universe during its history, this might leave observable traces, like circular patterns in the cosmic background. More fundamentally, proponents argue that the multiverse is not an ad hoc hypothesis invented to explain fine-tuning, but emerges naturally from independently motivated theories like inflation and string theory. If these theories are supported by other evidence, and if they naturally predict a multiverse, then the multiverse gains credibility as a consequence of well-tested physical principles, even if other universes remain beyond direct observation. The debate continues, with the multiverse representing one of the most profound and challenging ideas in contemporary cosmology. But beyond the scientific discussions, the multiverse concept offers a new perspective on cosmic self-creation, suggesting mechanisms by which universes might naturally form, evolve, and potentially even reproduce. One such mechanism comes from the theory of cosmic natural selection, proposed by physicist Lee Smolin. Noting the apparent fine-tuning of our universe for black hole production, Smolin suggested that universes might reproduce through black holes, with each black hole giving birth to a new universe with slightly varied physical parameters. If universes with more black holes have more cosmic offspring, then over many generations of universe creation, the multiverse would become dominated by universes whose physical laws maximize black hole production. Interestingly, many of the same properties that make a universe good at producing black holes, such as the ability to form stars, also make it hospitable for life. This might explain why our universe appears fine-tuned, not only for black holes, but also for complex chemistry and potentially life, without requiring either chance or design. Our universe would be the product of a kind of cosmic evolution, with its properties selected not for the emergence of life specifically, but for black hole formation, with life arising as a side effect of these same properties. Another possibility comes from considering quantum cosmology and the wave function of the universe. In this approach, developed by physicists like James Hartle, Stephen Hawking, and others, The entire universe is described by a quantum wave function that encompasses all possible configurations and histories. Rather than a single, deterministic history, the universe would exist as a superposition of many possible histories, with different probabilities assigned to each. The wave function would need to satisfy certain mathematical conditions, particularly what Hartle and Hawking called the no-boundary proposal, where the wave function is calculated by considering all possible universes that are compact, with no boundary in space or time. This approach suggests that universes with the highest probability would be those that begin in a smooth, low-entropy state and evolve according to the familiar laws of physics to produce the complex cosmos we observe. In this quantum cosmological framework, our universe would not be created in a conventional sense, but would represent the most probable history from a vast ensemble of possibilities inherent in the wave function of the universe. The wave function itself would not be created, but would exist mathematically as a solution to the Wheeler-DeWitt equation, which describes quantum gravity. The question of cosmic origins would transform from "how did our universe begin?" to "why do we experience this particular history from among all possibilities encoded in the universal wave function?" These approaches to cosmic reproduction and quantum selection hint at a universe that is in some sense self-creating and self-organizing. Rather than requiring an external creator or cause, the universe might arise through natural quantum processes, with its particular properties selected through a combination of random variation and cosmic evolution. The apparent design we observe would emerge not from conscious planning but from natural selection operating at the scale of universes, a kind of cosmic Darwinism. This perspective connects to broader philosophical questions about necessity and contingency in the cosmos. Traditionally, philosophers have distinguished between contingent facts, those that could have been otherwise, and necessary truths, those that could not have been otherwise. The existence and properties of our universe have typically been considered contingent, requiring explanation in terms of something external to the universe itself. But the multiverse suggests a different possibility. If all possible universes exist in some sense, then the multiverse as a whole might be necessary rather than contingent. The question would not be, why this universe rather than another, since all universes would exist, but why do we experience this particular universe? The anthropic principle provides the answer. We experience this universe because it is one of the relatively rare regions of the multiverse where creatures like us can exist. This shift from contingency to necessity transforms the traditional philosophical problem of creation. Instead of seeking an external cause for a contingent universe, we would recognize the multiverse itself as a necessary existence, with our particular universe representing one manifestation of this larger reality. The origin of the cosmos would not be an event in time, but a mathematical, logical, or quantum mechanical necessity inherent in the structure of reality itself. The multiverse also offers new perspectives on the apparent fine-tuning of physical constants. As we have discussed, observations indicate that many fundamental constants in our universe, such as the strength of the electromagnetic force, the mass of the electron, and the cosmological constant that describes the acceleration of cosmic expansion, appear calibrated with extraordinary precision to allow for structure and complexity. If any of these constants were slightly different, stars could not form, atoms would be unstable, or the universe would have collapsed or expanded too rapidly for structures to emerge. This apparent fine-tuning has been interpreted in various ways. Some see it as evidence for a designer who carefully calibrated the constants to allow for life. Others suggest there might be a deeper theory that explains why these constants must have the values they do, eliminating the appearance of fine-tuning. The multiverse offers a third perspective. If bubble universes form with random values for physical constants, and if there are enough such universes, then some will, by chance alone, have constants within the ranges that permit complexity and life. We inevitably find ourselves in such a universe, regardless of how rare they might be in the multiverse as a whole, because observers can only exist in universes compatible with their existence. This anthropic reasoning does not prove the existence of a multiverse, but it suggests that a multiverse would naturally explain the observed fine-tuning without requiring either extraordinary coincidence or conscious design. If correct, this would transform our understanding of our place in the cosmos. Our universe would not be uniquely designed for life, but would be one life-permitting bubble, in a vast and diverse multiverse. We would not be the purpose of creation, but fortunate inhabitants of a rare corner of the multiverse where complexity and consciousness can emerge. The implications extend beyond physics to philosophy and even theology. If the multiverse exists, with bubble universes forming naturally through eternal inflation, each sampling different physical laws, then the creation of our universe would be neither miraculous nor mysterious, but an expected consequence of quantum processes operating throughout the multiverse. The question would not be, why does our universe exist? But why would it not exist, given the generative processes operating in the multiverse? Some theologians and philosophers have suggested that the multiverse concept might be compatible with certain religious perspectives. The entire multiverse, rather than just our particular universe, might be the creation of a divine being who chose to actualize all possibilities rather than just one. Or perhaps divine action operates not by suspending natural laws but by influencing quantum events, guiding the evolution of the multiverse while respecting the autonomy of natural processes. Others see the multiverse as eliminating the need for a creator entirely, suggesting that the appearance of design and purpose in our universe can be explained through the combination of random variation and anthropic selection without requiring conscious planning. The debate continues, with the multiverse challenging traditional notions of cosmic uniqueness and purpose, while opening new avenues for understanding our place in a reality far vaster and more diverse than previously imagined. As we reflect on the multiverse concept and its implications for cosmic self-creation, we recognize that we stand at the frontier of human understanding, where science, philosophy, and even theology intersect. The multiverse represents a radical expansion of our cosmic perspective, suggesting that our entire observable universe, vast though it seems, might be a tiny fraction of a much larger and more diverse reality. If our universe is indeed one bubble in a vast multiverse, this transforms our understanding of cosmic origins. The creation of our universe would not be a singular, unique event requiring external causation, but one instance of a natural, ongoing process occurring throughout the multiverse. The fine-tuning we observe would not be the result of chance or design, but a selection effect, an inevitable consequence of the fact that observers can only exist in the rare universes compatible with their existence. This perspective suggests a cosmos that is in some sense self-creating and self-organizing, with bubble universes forming naturally through quantum processes, their properties varying randomly, and a kind of cosmic natural selection, potentially favoring universes that can reproduce through black holes or other mechanisms. The apparent design we observe would emerge not from conscious planning but from natural processes operating at the scale of universes. Yet even as the multiverse offers potential answers to age-old questions about cosmic origins and fine-tuning, it raises new questions of its own. If our universe is one bubble among many, what caused the first bubble to form? If eternal inflation has no beginning, how did it start? If the multiverse encompasses all possibilities, what determines which possibilities are actualized and experienced by conscious beings like ourselves? These questions may be pointing us toward even deeper principles, beyond the multiverse itself, principles that might explain why reality takes the form it does rather than some other form. As we continue our exploration, we will consider the role of cycles and repetition in cosmic history, the possibility that bounces rather than bangs characterize universe creation, and the evidence for echoes of previous cosmic cycles in the structure of our observable universe. The multiverse represents not the end of our inquiry, but a new beginning, a framework for understanding cosmic origins that encompasses the full richness and diversity of physical possibility. As we venture further into this vast landscape of possible realities, we may find clues not only to how our universe came to be, but to the deeper principles that govern existence itself, principles that might reveal how the cosmos creates and recreates itself endlessly through the infinite dance of quantum possibility. Time flows like a river, carrying us from past to future in what appears to be a one-directional journey, but might cosmic time itself flow in cycles rather than along a linear path? Could our universe be not the first or the only universe, but one phase in an endless sequence of expansion and contraction, death and rebirth? And might there be evidence, echoes of previous cosmic cycles, encoded in the radiation and structure we observe in our current universe? These questions touch on some of the oldest cosmological ideas in human culture, while connecting to cutting-edge developments in theoretical physics. Cyclical models of the cosmos have appeared in many ancient traditions, from Hindu cosmology, with its endless cycles of creation and destruction, to certain Native American worldviews that envision time as circular rather than linear. Now, modern physics offers mathematical frameworks that might revive these ancient intuitions in scientific form, suggesting that bounces rather than bangs could characterize the fundamental nature of cosmic history. We begin our exploration with the standard Big Bang model, which describes our universe as expanding from an extremely hot, dense state about 13.8 billion years ago. This model, supported by extensive observational evidence, traces cosmic history from the first fraction of a second through the formation of light elements, the recombination of electrons and nuclei to form neutral atoms, the cosmic dark ages, and the eventual emergence of stars, galaxies, and larger structures. As successful as this model has been, it leaves open the question of what, if anything, preceded the Big Bang. Did the universe truly begin at that moment, or was the Big Bang merely a transition, a rebirth of a pre-existing cosmos? The mathematics of general relativity, when applied to the early universe, suggests a singularity, a point of infinite density and temperature, where the equations themselves break down. But this mathematical breakdown does not necessarily mean that nothing existed before. It might simply indicate that we need new physics to describe what happened at that boundary. Several theoretical frameworks now suggest that our universe might have emerged from the collapse of a previous universe, with the apparent Big Bang singularity replaced by a cosmic bounce. One such framework comes from loop quantum cosmology, an application of loop quantum gravity to the entire universe. Loop quantum gravity attempts to unify general relativity with quantum mechanics by proposing that space itself has a discrete, quantized structure at the smallest scales, like a fabric woven from tiny loops. When these quantum principles are applied to the cosmos as a whole, they suggest that as a contracting universe reaches extremely high but finite densities, quantum gravitational effects create a repulsive force that prevents further collapse. Instead of reaching a singularity of infinite density, the contraction slows, stops, and reverses, producing a bounce into a new phase of expansion. The Big Bang would not mark the beginning of everything, but would represent a transition, a cosmic rebirth from a previous phase. The mathematics of loop quantum cosmology shows that such a bounce would preserve certain aspects of the pre-bounce universe while changing others. The arrow of time would reverse at the bounce, with entropy increasing in both directions away from the bounce. Matter and energy from the previous phase would be carried over into the new phase, though transformed by the extreme conditions at the bounce, and certain large-scale patterns might persist, potentially leaving observable signatures in our current universe. Another approach to cosmic bounces comes from what physicists call ekpyrotic or cyclic models, developed by Paul Steinhardt, Neil Turok, and others. These models, inspired by concepts from string theory and M-theory, suggest that our universe exists as a three-dimensional membrane or brain floating within a higher dimensional space. The Big Bang might have resulted from a collision between our brain and another, releasing enormous energy that drove the expansion and evolution of our universe. In the ekpyrotic scenario, these brain collisions would occur repeatedly, creating an endless cycle of expansion, cooling, contraction, collision, and renewed expansion. Each cycle might last trillions of years, with galaxy formation and biological evolution occurring during the middle phases, followed by a gradual emptying of matter from the visible universe, and finally a contraction leading to the next collision and the birth of a new cycle. A key feature of these models is that they do not require the extreme conditions of inflation to explain the uniformity and flatness of our universe. Instead, the slow contraction phase before the bounce naturally produces a uniform, flat geometry, addressing the same puzzles that inflation was designed to solve, but through different mechanisms. This offers an alternative to the inflationary paradigm, with distinct observational predictions that might allow us to distinguish between these competing models. A third framework for cosmic cycles comes from conformal cyclic cosmology, developed by mathematical physicist Roger Penrose. This model proposes a subtle connection between the far future of one universe and the beginning of the next. As a universe ages and expands, matter gradually breaks down. Protons may decay over timescales of 10 to the power of 34 years or longer. Black holes evaporate through Hawking radiation over even longer periods. Eventually, all that remains are massless particles like photons traveling through an effectively infinite space. Penrose recognized a mathematical similarity between this far future state and the hot, dense beginning of a new universe. In both cases, particles are effectively massless, either because they actually have no mass, like photons, or because their rest mass becomes negligible compared to their kinetic energy at extremely high temperatures. This allows Penrose to apply a mathematical transformation called a conformal mapping to connect the infinite future of one universe with the Big Bang of the next. In this model, the transition from one cosmic cycle to the next occurs not through a spatial bounce or contraction, but through a rescaling of all physical quantities. What appears as an infinite, empty universe from one perspective becomes a hot, dense beginning from another. Time continues forever in one sense, yet also restarts with each new cycle. The end of one universe becomes the beginning of the next, not through a spatial collapse and re-expansion, but through a conformal transformation that preserves certain mathematical relationships while rescaling others. These diverse approaches to cosmic cycles share a common theme: the idea that what we call the Big Bang might not be the absolute beginning, but a transition, a rebirth of a pre-existing cosmos in a new form. If any of these models are correct, the history of reality would extend far beyond the 13.8 billion years we can directly trace, encompassing previous cosmic cycles with their own stars, galaxies, and perhaps even life, stretching infinitely into the past, as well as the future. This perspective transforms our understanding of cosmic self-creation. Rather than requiring our universe to emerge from absolute nothing in a single event, these cyclical models suggest that reality continually recreates itself through natural physical processes. The universe would not have a beginning in the conventional sense, but would exist eternally in cycles of expansion and contraction, death and rebirth. But is there any evidence for these cosmic cycles? Might there be observable signatures, echoes of previous cycles imprinted on the radiation and structure we see in our current universe? Several teams of physicists have proposed potential tests for cyclical models, searching for patterns that might have survived the transition from one cycle to the next. In conformal cyclic cosmology, Penrose has suggested that supermassive black hole mergers in the previous cosmic cycle might have left circular patterns in the cosmic microwave background radiation of our current universe. These concentric circles would appear as regions of slightly different temperature, reflecting the enormous energy released when black holes collided in the previous cycle. Penrose and his colleagues have claimed to find such patterns in the cosmic microwave background data from the Wilkinson Microwave Anisotropy Probe and the Planck satellite, though other researchers have disputed these findings, suggesting they might be statistical flukes or artifacts of the analysis method. In bouncing models based on loop quantum cosmology, the extreme compression at the bounce might leave imprints on the spectrum of gravitational waves and on the distribution of galaxies in our universe. The spectrum of primordial gravitational waves, ripples in space-time produced in the earliest moments, would differ between a pure inflationary model and a bounce model. Future gravitational wave detectors, both in space and on Earth, might be able to distinguish between these possibilities, providing evidence for or against a cosmic bounce. Similarly, in ekpyrotic and cyclic models, the slow contraction phase before the brane collision would produce a distinctive pattern in the primordial gravitational wave spectrum and in the distribution of density fluctuations. These patterns differ from the predictions of standard inflationary models, offering potential observational tests to distinguish between these competing frameworks. While conclusive evidence remains elusive, the possibility of testing these cyclical models highlights a crucial aspect of modern cosmology. Even when dealing with events that occurred before the Big Bang or that involve other universes beyond our observable horizon, the theories may still make specific, testable predictions about observable features of our current universe. The boundary between empirical science and metaphysical speculation is not fixed, but continues to shift as our theories become more sophisticated and our observations more precise. The concept of cosmic cycles connects to deeper questions about the nature of time itself. In many of these models, the arrow of time, the apparent one-directional flow from past to future, would reverse at the bounce or transition between cycles. Entropy, a measure of disorder that normally increases over time according to the second law of thermodynamics, would reach a minimum at the bounce and increase in both temporal directions away from it. This suggests a universe symmetric in time when viewed at the largest scales, with each cosmic cycle beginning in a low entropy state and evolving toward higher entropy. Yet we experience time as flowing in only one direction, with the past fixed and the future open. This apparent contradiction highlights how our experience of time might be local rather than universal, arising from the particular conditions in our corner of the cosmos rather than reflecting a fundamental asymmetry in physical law. The philosopher Hugh Price has explored this perspective, suggesting that the apparent arrow of time might be a result of our particular vantage point within the universe, rather than a fundamental feature of reality. Just as Earth once seemed to be at the center of the cosmos, until the Copernican revolution revealed it to be one planet among many in orbit around the Sun, our experience of time as flowing in one particular direction might reflect our limited perspective rather than a cosmic truth. These considerations connect to what physicists call the problem of initial conditions. Why did our universe begin in a state of such extraordinarily low entropy, such high order? The second law of thermodynamics tells us that entropy tends to increase over time in closed systems. If the universe began in a generic high entropy state, we would not observe the rich structure and complexity we see today. Stars would not form, galaxies would not organize, and life would be impossible. The low entropy of the early universe appears to require extraordinarily special initial conditions, a cosmic coincidence that demands explanation. Inflationary models address this partially by explaining the uniformity and flatness of the early universe, but they do not fully resolve why inflation itself began in just the right state to produce our observed cosmos. Cyclical models offer a potential resolution to this puzzle. If each cosmic cycle naturally ends with a high entropy state but begins with a low entropy state, and if the transition between cycles resets entropy in some sense, then the special initial conditions of our universe would not be coincidental, but would result naturally from the physics of the cosmic transition. The problem of initial conditions would be resolved by embedding our observable cosmic history within a larger cyclical framework. This perspective connects to broader philosophical questions about necessity and contingency in the cosmos. Traditionally, the particular state of our universe has been considered contingent, dependent on initial conditions that could have been different. But if cyclical models are correct, and if the transition between cycles naturally produces certain conditions in the new cycle, then what appears contingent from our limited perspective might be necessary within the larger cyclical framework. The philosopher Immanuel Kant explored similar themes in his Critique of Pure Reason, suggesting that when human reason attempts to comprehend the absolute beginning or endless duration of the world, it encounters inevitable contradictions, which he called antinomies. Perhaps these antinomies reflect the limitations of human understanding when confronted with a reality that transcends our categories of thought, a cosmos that is neither finite nor infinite in the conventional sense, but cycles endlessly between different states. Modern cyclical models give new meaning to Kant's insights, suggesting mathematical frameworks that might resolve these apparent contradictions. A universe that cycles endlessly would have no absolute beginning, yet would not be infinitely old in the conventional sense, as each cycle would have a finite duration. Time would be both linear within each cycle and circular when viewed across cycles, a conception that transcends the simple dichotomy between finite and infinite cosmic history. These philosophical considerations highlight the profound implications of cyclical models for our understanding of cosmic self-creation. If the universe cycles endlessly, with each cycle emerging from the remnants of the previous one, then creation would not be a singular event, but an ongoing process, a perpetual rebirth through natural physical mechanisms. The universe would create itself not once but continually, a self-sustaining system with no beginning or end, no external cause or creator. This cyclical perspective resonates with certain religious and philosophical traditions, while transforming them in light of modern physics. Hindu cosmology speaks of cosmic cycles called kalpas, with universes being created and destroyed in an endless sequence. Buddhist philosophy envisions reality as an endless process of becoming rather than as fixed being. And certain Western philosophical traditions, from the pre-Socratic philosopher Heraclitus to process philosophers like Alfred North Whitehead, have emphasized becoming over being, process over substance, as the fundamental nature of reality. Modern cyclical models give mathematical expression to these ancient intuitions, suggesting that the cosmos might indeed be an endless process of becoming rather than a static entity created at a specific moment. The universe would not be a noun but a verb, not a thing but a process, continually recreating itself through natural physical mechanisms encoded in the laws of quantum gravity. Yet even as cyclical models resolve certain puzzles about cosmic origins, they raise new questions of their own. What drives the cycles? Why does the universe bounce rather than collapse to a singularity? Why these particular cycles with these particular properties rather than others? These questions point toward deeper principles that might govern the cyclical dynamics of the cosmos. One approach to these questions comes from considering the role of entropy and information in cosmic evolution. If entropy increases throughout each cosmic cycle, approaching a maximum at the end, and if the transition to the next cycle somehow resets entropy to a minimum, this suggests a kind of cosmic memory loss, where information from the previous cycle is partially erased or transformed during the transition. Physicist Sean Carroll has explored this perspective, suggesting that the arrow of time and the increase of entropy might be connected to quantum entanglement between different regions of the universe. As the universe expands, regions that were once in close contact become separated, with quantum information spread across vast distances. This spreading of information might play a role in the apparent increase of entropy over time, with implications for how information might be processed or transformed during a cosmic transition. Another approach focuses on the role of quantum fluctuations in driving cosmic cycles. In certain bouncing models, quantum fluctuations near the bounce point might introduce an element of randomness into each new cycle, ensuring that no two cycles are exactly identical. The cosmos would not simply repeat itself, but would explore different possibilities in each cycle, a kind of cosmic evolution driven by quantum indeterminacy. This quantum perspective connects to questions about the role of observers in the cosmos. In quantum mechanics, observation plays a crucial role, with the act of measurement appearing to collapse quantum superpositions into definite states. Applied to the universe as a whole, this suggests that conscious observers might play a role in determining which potential realities become actualized from the vast landscape of quantum possibilities. The physicist John Wheeler captured this idea in his concept of the participatory universe, suggesting that observations in the present might influence how we describe the past, even the distant past, before conscious observers existed. In his delayed choice experiments, actions in the present seem to affect how we must describe the behavior of particles in the past, suggesting a kind of retrocausality that challenges our conventional understanding of temporal sequence. Applied to cyclical models, these insights suggest that observers in one cosmic cycle might influence, through quantum effects, the conditions of the next cycle. The cosmos would not simply repeat mechanically, but would evolve through a complex interplay between physical processes and observation, a kind of cosmic learning process unfolding across cycles. This perspective connects to what theorist Lee Smolin calls cosmological natural selection, the idea that universes might evolve through a process analogous to biological evolution. If black holes in one universe give birth to new universes with slightly varied physical parameters, and if universes with more black holes have more cosmic offspring, then over many cycles, the multiverse would become dominated by universes whose physical laws maximize black hole production. Interestingly, many of the same properties that make a universe good at producing black holes, such as the ability to form stars and galaxies, might also make it hospitable for complex chemistry and potentially life. This might explain why our universe appears fine-tuned for both black holes and life, without requiring either chance or design. Our universe would be the product of a kind of cosmic evolution, with its properties selected not for life specifically, but for black hole formation, with life arising as a side effect of these same properties. These evolutionary perspectives transform our understanding of cosmic purpose and design. Rather than requiring a pre-existing plan or blueprint for the cosmos, they suggest that purpose and design might emerge naturally through evolutionary processes, operating at the cosmic scale. The universe would not be designed for any particular outcome, but would explore different possibilities through cycles of creation and destruction, with certain patterns persisting or amplifying through a kind of cosmic natural selection. This evolutionary framework connects to broader philosophical questions about teleology, the idea that natural processes are directed toward particular ends or goals. Traditional Western philosophy and theology often assumed that purpose must precede process, that design requires a designer, that goals must be established before they can be pursued. But modern evolutionary theory has challenged this assumption, showing how purpose-like features can emerge naturally from purposeless processes through feedback mechanisms and selection effects. Applied to the cosmos as a whole, this suggests that what appears to be cosmic design might emerge naturally from cyclic processes operating over vast timescales. The fine-tuning we observe would not reflect pre-existing goals or purposes, but would result from a kind of cosmic learning process, with successful patterns persisting and unsuccessful ones disappearing through natural selection at the universal scale. This perspective offers a middle path between the traditional dichotomy of chance and design in explaining cosmic order. The universe would be neither a random accident nor the product of conscious planning, but the result of a natural evolutionary process, a self-organizing system that explores different possibilities through cycles of creation and destruction, gradually developing patterns that permit increasing complexity and potentially consciousness. Such a self-organizing, cyclical cosmos would truly create itself, not once but continually, through natural processes that require no external cause or creator. The apparent design we observe would emerge from within rather than being imposed from without, a product of the universe's own self-organizing dynamics operating across countless cosmic cycles. As we reflect on these cyclical models and their implications for cosmic self-creation, we recognize that we stand at the frontier of human understanding, where science, philosophy, and even theology intersect. The mathematics of quantum gravity and cosmology suggest possibilities that transcend our conventional categories, a universe that is neither created nor eternal in the traditional sense, but that cycles endlessly between different states, continually recreating itself through natural physical processes. This perspective does not eliminate mystery but transforms it. The wonder is not that something impossible occurred, requiring supernatural intervention, but that the fabric of reality itself contains the potential for endless cycles of creation and destruction, a cosmos that renews itself perpetually through bounces rather than bangs, through transitions rather than terminations. As we continue our exploration, we will examine another frontier of cosmic self-creation, the role of consciousness and observation in quantum reality. We will consider whether consciousness might play a deeper role in the creation and evolution of the cosmos, whether the observer effect in quantum mechanics might have cosmological implications, and whether the universe might create itself, in some sense, through being observed and understood by the conscious beings it produces. Perhaps in the interplay between observers and observed, between consciousness and cosmos, we will find deeper clues to how a universe might create itself from within, rather than being created from without. The cosmos unfolds across billions of light years, with stars and galaxies born and dying over billions of years, processes seemingly indifferent to whether anyone is watching. Yet one of the most profound discoveries of modern physics suggests that observation itself plays a crucial role in determining physical reality. The quantum world, which underlies all of physical existence, appears to be influenced by the act of observation, with quantum systems existing in states of possibility, rather than actuality until they are measured or observed. This observer effect in quantum mechanics raises a profound question. If observation helps determine reality at the quantum level, and if the entire cosmos ultimately rests on quantum foundations, might consciousness play a deeper role in the creation and evolution of the universe than we have previously imagined? Could the universe, in some sense, create itself through being observed and understood by the conscious beings it produces? In this chapter, we explore these extraordinary possibilities, examining how consciousness and observation might contribute to cosmic self-creation. We will consider the observer effect in quantum mechanics, the anthropic principle in cosmology, the participatory universe concept proposed by physicist John Wheeler, and the potential implications of these ideas for understanding how a universe might create itself not from outside but from within, through a kind of cosmic self-observation and self-awareness. Our exploration begins with the famous double-slit experiment, which reveals the observer effect in its most striking form. When electrons or photons are fired one at a time through a barrier with two parallel slits, they create an interference pattern on the detector screen, as if each particle passes through both slits simultaneously, interfering with itself like a wave. Yet if we place detectors at the slits to observe which path each particle takes, the interference pattern disappears, and the particles behave like discrete bullets, each passing through exactly one slit. This experiment, replicated countless times with increasingly sophisticated methods, demonstrates that the act of observation appears to change how quantum systems behave. When unobserved, particles exist in superpositions, mathematical states representing multiple possibilities simultaneously. When observed, these superpositions collapse into definite states, with particles appearing at specific locations rather than spread across possibilities. The interpretation of this phenomenon remains one of the most contested areas in physics. The Copenhagen interpretation, developed by Niels Bohr, Werner Heisenberg, and others in the early 20th century, suggests that quantum systems exist as probability waves until observed, at which point they collapse into definite states. This places observation in a special role as the boundary between quantum possibility and classical actuality. Other interpretations, like the many worlds interpretation proposed by Hugh Everett, suggest that no collapse occurs. Instead, each possible outcome happens in a different branch of reality, with the universe splitting into parallel versions at each quantum event. Observers in each branch experience only one outcome, creating the illusion of collapse, while in reality all possibilities manifest in different branches of an ever-branching multiverse. Still, other interpretations, like the pilot wave theory of David Bohm, propose that particles always have definite positions, guided by real physical waves, with the apparent indeterminacy of quantum systems resulting from our ignorance of the exact initial conditions, rather than from any inherent quantum fuzziness. In this view, observation does not cause collapse, but simply reveals pre-existing facts about the system. These diverse interpretations highlight the ongoing mystery surrounding the role of observation in quantum mechanics. After more than a century of debate, physicists still disagree about what happens during measurement and what role, if any, consciousness might play in the process. Yet regardless of interpretation, the empirical fact remains: when we observe quantum systems, they behave differently than when unobserved, a phenomenon with potential implications for cosmic self-creation. The quantum observer effect gains cosmic significance when we consider the role of quantum processes in the early universe. During the first fraction of a second after the Big Bang, when the entire observable universe was smaller than an atom, quantum effects would have dominated, with the fabric of space-time itself subject to quantum uncertainty. The initial conditions that set the course for cosmic evolution, including the distribution of matter and energy that would eventually form galaxies and stars, might have been determined by quantum processes involving superpositions and collapse. If quantum collapse requires observation, as the Copenhagen interpretation suggests, this raises a profound question. Who or what observed the early universe, collapsing its quantum state into the specific configuration that led to our current cosmos? If observation plays a role in determining quantum reality, and if the early universe was a quantum system, how could its state have collapsed before any observers existed to measure it? One potential resolution to this paradox comes from what physicists call decoherence, the process by which quantum systems lose their coherence, their ability to maintain superpositions, through interactions with their environment. When a quantum particle interacts with other particles in its surroundings, information about its state spreads through the environment, making the superposition practically unobservable. The system appears to have collapsed into a definite state, even without a conscious observer making a measurement. Decoherence explains why macroscopic objects like baseballs and planets behave according to classical physics rather than quantum mechanics, despite being composed of quantum particles. The countless interactions between particles in these objects cause rapid decoherence, making quantum effects unobservable at the macroscopic scale. This might suggest that the early universe could have undergone a similar process, with quantum superpositions decohering through interactions within the expanding cosmos, without requiring conscious observers. Yet decoherence does not fully resolve the measurement problem in quantum mechanics. It explains why superpositions become practically unobservable, but does not address the deeper question of whether these superpositions truly collapse into single definite states or continue to exist in some unobservable form. Different interpretations of quantum mechanics offer different answers to this question, with implications for the role of observation in cosmic evolution. Another approach to the role of observation in cosmic origins comes from the anthropic principle, the idea that our observations of the universe are necessarily constrained by the conditions required for observers like us to exist. The anthropic principle comes in different forms, from the weak version, which simply notes that our observations are biased by the requirement that we exist to make them, to the strong version, which suggests that the universe must have the properties necessary for observers to emerge at some point in its history. In its most basic form, the anthropic principle helps explain why we observe a universe so exquisitely tuned for life. If the fundamental constants of nature, like the strength of the electromagnetic force or the mass of the electron, were slightly different, stars could not form, chemistry would not work, or structures would not emerge. The fact that we observe these constants to have precisely the values that allow for our existence is not surprising, regardless of how improbable these values might be, because we could not exist to observe a universe with different values. But some theorists have proposed a more radical version of the anthropic principle, suggesting that observation might play a causal role in determining cosmic properties. In this view, the universe has the properties it does, not merely because observers can only exist in universes with these properties, but because observation itself helps establish these properties through quantum effects operating at the cosmic scale. The physicist John Wheeler, who coined the term black hole and made fundamental contributions to quantum mechanics and relativity, developed this idea into what he called the participatory anthropic principle. Wheeler suggested that quantum mechanics implies a universe that is in some sense self-observing and self-synthesizing, with observers playing a crucial role in transforming quantum possibilities into actualities, not just in laboratory experiments but at the cosmic scale. Wheeler captured this idea in his famous phrase, "it from bit," suggesting that physical reality, it, emerges from information, bit, through a process that involves observation and measurement. In this view, the universe is fundamentally informational rather than material, with physical objects and properties emerging from networks of binary observations, yes or no answers to questions posed by observers within the universe. Wheeler illustrated this participatory perspective with a thought experiment he called the delayed choice experiment, later realized in actual laboratory tests. In this experiment, the observer can choose whether to measure which path a photon takes through an apparatus, or to observe its wave interference pattern, with this choice made after the photon has presumably already passed through the critical part of the apparatus. The results suggest that the observer's delayed choice affects how we must describe the photon's earlier behavior, as if the present observation influences the past. Extending this insight to cosmology, Wheeler proposed what he called the participatory universe, suggesting that the universe exists as quantum potential until observed, with observers themselves emerging from this potential through a kind of cosmic self-observation. In a striking phrase, he suggested that the universe requires observers so that it may establish itself as universe, a kind of cosmic bootstrap operation where existence itself emerges through being observed. The mathematics of quantum cosmology, particularly the Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, offers some support for this perspective. In this framework, the universe is described by a wave function that encompasses all possible configurations and histories. Rather than a single deterministic history, the universe would exist as a superposition of many possible histories, with different probabilities assigned to each. When observers make measurements, they effectively select a particular branch of this universal wave function, experiencing one history from among the many possibilities. The universe would not have a single, objective history independent of observation, but would exist as a quantum superposition of possible histories, with observation helping to determine which history is experienced, and thereby becomes actual from the perspective of those observers. This participatory perspective transforms our understanding of cosmic origins. Rather than imagining the universe being created at a specific moment by some external cause, we might envision it as emerging gradually through a process of self-observation and self-synthesis, with each observation by conscious beings within the universe helping to establish its nature and history. The creation of the universe would not be an event in the past, but an ongoing process in which we participate through our observations and measurements. This perspective resonates with certain philosophical traditions, particularly the process philosophy of Alfred North Whitehead, who suggested that reality is not composed of static substances, but of events and processes, with each moment representing a creative advance into novelty. In Whitehead's view, the universe continually creates itself through what he called prehension, a kind of proto-awareness through which each entity in the cosmos relates to all others, integrating past events into present experiences. Applied to quantum cosmology, this process perspective suggests that the universe might create itself not once but continually, with each quantum observation contributing to the ongoing creation of reality. The Big Bang would not be the creation of everything from nothing but one event within a more fundamental process of cosmic self-creation through observation and information processing. This informational perspective on cosmic origins connects to recent developments in quantum information theory, which suggests that information may be more fundamental than either matter or energy. Work by researchers like Eric Verlinde indicates that gravity itself might be an emergent phenomenon, arising from the entanglement of quantum information, rather than representing a fundamental force. If correct, this would mean that space-time, and the gravitational field that shapes it, emerges from more fundamental quantum information processes. Similarly, recent work on quantum error correction codes suggests unexpected connections between quantum information theory and fundamental physics. Researchers have found that certain quantum error correction codes, mathematical structures designed to protect quantum information from decoherence, appear naturally in the equations of string theory and in the behavior of black holes. This suggests that the fabric of spacetime itself might be a kind of quantum error correction code, a structure that preserves information across scales from the quantum to the cosmic. These developments support Wheeler's intuition that information, observation, and measurement might be fundamental to physical reality, with the universe emerging from networks of binary observations, yes or no answers to questions posed through measurement. The cosmos would not be created from outside, but would create itself from within through the processing of quantum information and the collapse of quantum possibilities into actualities through observation. This self-creating participatory universe would not require an external creator or first cause. Instead, it would bootstrap itself into existence through a kind of cosmic self-observation, with conscious beings within the universe playing a crucial role in this process. Rather than being passive spectators of a pre-existing reality, observers would be active participants in the creation and evolution of the cosmos. This perspective raises profound questions about the nature of time and causality in the quantum realm. If present observations can influence how we describe past events, as the delayed choice experiments suggest, then perhaps the traditional view of causality, with causes preceding effects in a linear sequence, breaks down at the quantum level. The relationship between past, present, and future might be more complex and interconnected than our everyday experience suggests, with quantum effects allowing for a kind of retrocausality that transcends simple temporal sequence. Applied to cosmic origins, this suggests that observers in the present might influence not just how we describe the past, but how the past actually manifested from quantum possibilities. Our observations now might help determine which of many possible cosmic histories occurred, not by changing the past in a science fiction sense, but by selecting which branch of the universal wave function becomes actualized from our perspective. This participatory view of cosmic creation resonates with certain religious and spiritual traditions while transforming them in light of quantum insights. The universe would not be created by a deity external to itself, but would create itself through the emergence of consciousness and observation within it. What some traditions call God might be reconceived as the self-creating, self-observing cosmos, rather than as a being separate from the universe. The physicist Freeman Dyson captured this perspective when he wrote, "In some sense, the universe knew we were coming. The laws of nature seem remarkably well designed to allow for the emergence of complexity, consciousness, and observation. Rather than seeing this as evidence for an external designer, the participatory view suggests that the universe has the properties it does precisely because it creates itself through self-observation, with conscious beings emerging naturally as part of this self-creative process. This self-creative, participatory perspective also offers a potential resolution to the problem of cosmic fine-tuning. The fundamental constants of nature appear calibrated with extraordinary precision to allow for complexity and life, a fact that has been cited as evidence for either incredible cosmic luck, an external designer, or the existence of a multiverse with varied physical laws. The participatory view suggests another possibility, that the universe has the properties it does because these properties allow it to observe itself through the conscious beings it produces. Rather than the anthropic principle merely noting that we can only observe a universe compatible with our existence, the participatory anthropic principle suggests that observation itself helps establish the properties of the universe through quantum effects. The cosmos would not be designed for observers, but would create itself through becoming observable, through transforming quantum possibilities into actualities via the emergence of consciousness and measurement. This perspective transforms how we understand our place in the cosmos. Rather than being accidental byproducts of blind physical processes or the intended outcomes of a pre-existing plan, conscious beings would be integral to the universe's self-creation and self-understanding. Consciousness would not be an epiphenomenon, a mere side effect of physical processes, but a fundamental aspect of cosmic evolution, a means by which the universe observes itself and thereby establishes its own nature and history. Some theorists have proposed more specific mechanisms by which consciousness might contribute to cosmic self-creation. The neuroscientist and physicist Roger Penrose, working with anesthesiologist Stuart Hameroff, has suggested that quantum effects in brain microtubules might play a role in consciousness, providing a link between quantum physics and mental processes. While controversial, this orchestrated objective reduction theory proposes that consciousness involves the orchestrated collapse of quantum superpositions in neural structures, a process that might connect individual consciousness to quantum processes at the cosmic scale. Others, like philosopher David Chalmers and physicist Giulio Tononi, have proposed that consciousness might be a fundamental property of reality, as basic as mass or charge, rather than an emergent phenomenon arising solely from neural complexity. This panpsychist perspective suggests that consciousness, in some proto-form, might exist throughout the cosmos, with complex forms like human awareness representing highly organized manifestations of a more widespread phenomenon. If consciousness is indeed fundamental rather than emergent, this would further support the participatory view of cosmic evolution. The universe would not need to produce consciousness from unconscious matter, but would express consciousness in increasingly complex forms throughout its development. The human mind would be one manifestation of a more ubiquitous cosmic awareness, a way for the universe to observe itself with particular depth and clarity. These perspectives on consciousness and its role in cosmic self-creation remain speculative, at the frontier of physics, philosophy, and neuroscience. They challenge conventional assumptions about the relationship between mind and matter, observer and observed, creator and created. Yet they emerge naturally from the empirical discovery of the observer effect in quantum mechanics, combined with the insights of quantum cosmology and information theory. The philosopher Thomas Nagel has argued that any complete theory of reality must account not only for physical phenomena, but also for the emergence of mind and consciousness. If consciousness is a natural feature of the universe, as it evidently is, then our fundamental theories should explain how and why consciousness arises, not simply assume it as an inexplicable addition to physical processes. The participatory view of cosmic evolution offers a framework for understanding consciousness, not as separate from physical reality, but as integral to its creation and evolution. This integration of consciousness into our understanding of cosmic evolution connects to what philosopher Bernardo Kastrup calls analytic idealism, the view that consciousness is the fundamental reality from which matter emerges, rather than the other way around. In this perspective, physical reality represents the outside view of a fundamentally mental process. the way consciousness appears when observed externally rather than experienced internally. Applied to cosmic origins, this idealist perspective suggests that the universe might have created itself not through physical processes as conventionally understood, but through consciousness and observation. The physical universe would be the exterior aspect of a fundamentally mental reality, with cosmic evolution representing the development of universal consciousness rather than merely the rearrangement of unconscious matter. While such idealist perspectives remain minority views in contemporary physics, they highlight how the observer effect in quantum mechanics raises profound questions about the relationship between mind and matter, consciousness and cosmos. If observation plays a role in determining physical reality at the quantum level, and if the entire cosmos ultimately rests on quantum foundations, then consciousness cannot be easily dismissed as irrelevant to understanding cosmic origins and evolution. The participatory universe concept also connects to information-based approaches to physics and cosmology. If information is more fundamental than either matter or energy, as some theoretical frameworks suggest, then the creation and processing of information through observation and measurement might be central to understanding how the universe creates and maintains itself. The physicist James Gates has discovered error-correcting codes embedded in the equations of supersymmetry, a proposed extension of the standard model of particle physics. These codes, similar to those used in web browsers and internet communications, appear naturally in the mathematics of fundamental physics, suggesting that the cosmos might be structured like a vast computer program, with information processing at its core. Similarly, the work of theoretical physicist Juan Maldacena on what physicists call the ADS-CFT correspondence suggests deep connections between quantum information theory and the structure of space-time. This mathematical relationship, which connects a gravitational theory in a space with a quantum theory on its boundary, indicates that space-time itself might emerge from quantum entanglement, the non-local correlations between quantum systems. These information-theoretical approaches support the idea that the universe might create itself through the processing of quantum information, with observation and measurement playing crucial roles in this process. The cosmos would not be a static entity, but a dynamic information processing system, continually creating itself through the transformation of quantum possibilities into actualities via observation and entanglement. This informational perspective transforms our understanding of cosmic self-creation. Rather than requiring an external cause or creator, the universe might create itself through internal information processes, with conscious observation serving as one crucial mechanism by which quantum possibilities become actualities. The creation of the cosmos would not be an event in the distant past, but an ongoing process in which we participate through our observations and measurements. As we reflect on these participatory perspectives on cosmic self-creation, we recognize that we stand at the frontier of human understanding, where physics, philosophy, and even spirituality intersect. The observer effect in quantum mechanics reveals a universe more strange and wonderful than our ancestors could have imagined, a reality in which consciousness and observation play crucial roles in determining the very fabric of existence. If the participatory universe concept is correct, even partially, then the creation of the cosmos would not be separate from our observation and understanding of it. In observing the universe, in measuring its properties and contemplating its nature, we would be participating in its ongoing self-creation. Every scientific experiment, every astronomical observation, every philosophical reflection on existence would represent the universe coming to know itself, to create itself, through the conscious beings it has produced. This perspective does not eliminate mystery but transforms it. The wonder is not that something impossible occurred, requiring supernatural intervention, but that the fabric of reality itself contains the potential for consciousness and self-observation, a cosmos that creates itself partially through being observed and understood by the conscious beings it produces. As we continue our exploration, we will examine whether asking why the universe exists might be meaningless from certain scientific perspectives. We will consider the concept of mathematical necessity, the idea that the cosmos might exist because its fundamental structure could not be otherwise. And we will explore whether the laws of physics themselves might be self-selecting, emerging naturally from deeper principles rather than requiring calibration or design. In these mathematical and logical approaches to cosmic origins, we may find further clues to how a universe might create itself, not through external causation, but through internal necessity and self-consistency. Why is there something rather than nothing? Why does the universe exist at all? Why these physical laws rather than others? These profound questions have echoed through human history, driving philosophical inquiry, religious contemplation, and scientific investigation. They represent perhaps the deepest possible form of questioning, seeking reasons for existence itself. Yet some scientists and philosophers now suggest that these why questions, when applied to the universe as a whole, might be fundamentally misplaced or even meaningless. In this chapter, we explore the possibility that asking why the universe exists might be like asking what is north of the North Pole, a question that seems grammatically valid but contains assumptions that make it unanswerable in principle. We will consider how certain scientific frameworks render traditional why questions problematic, how the concept of explanation itself might break down at the cosmic scale, and how what initially seems like an intellectual retreat might actually represent a profound advance in our understanding of reality itself. Our exploration begins with a careful examination of what we mean by why questions and how they function in different contexts. When we ask why something happened, we typically seek causes that preceded the event, circumstances that made it possible, or purposes that motivated it. Why did the apple fall? Because gravity pulled it downward. Why does water boil at 100 degrees Celsius? Because at that temperature, the kinetic energy of water molecules overcomes the forces binding them together. Why did the person cross the road? To reach the other side. These different forms of why questions, causal, constitutive, and teleological, work well within the universe, where we can identify chains of cause and effect, underlying structures and forces, or goals and intentions. But difficulties arise when we try to apply these same patterns of questioning to the universe as a whole. If causes must precede their effects, what could cause the beginning of time itself? If explanations require more fundamental principles, what principles could be more fundamental than the laws of physics that govern all of reality? If purposes require minds to conceive them, what mind could have existed before the universe to give it purpose? The physicist Stephen Hawking captured this dilemma in A Brief History of Time when discussing what came before the Big Bang. He compared asking this question to asking what is north of the North Pole. The question seems sensible based on our everyday experience, where we can always go farther north, but it contains a hidden assumption that breaks down at the pole itself. Similarly, asking what caused the Big Bang assumes that time extends before the beginning, allowing for a causal sequence. But if time itself began with the Big Bang, this assumption fails. This insight suggests that certain why questions about cosmic origins might be category errors, attempts to apply concepts that work within the universe to the universe as a whole. The universe, by definition, includes all of physical reality. There is no outside, no before, no more fundamental reality from which it emerged. Traditional causal explanations, which rely on identifying prior conditions or more basic principles, may simply not apply to existence itself. Several frameworks in modern physics and cosmology support this perspective. The inflationary multiverse model, which we explored in earlier chapters, suggests that our universe might be one bubble in an eternally inflating multiverse, with new bubble universes continually forming through quantum fluctuations in the inflating space. In this framework, asking for the cause of the multiverse becomes problematic, as the process of bubble formation has no beginning in the conventional sense. It extends eternally into the past as well as the future, with no first bubble and no moment of creation. Mathematically, the eternal inflation model can be shown to be geodesically incomplete towards the past, meaning that while the model has no beginning in terms of time, its space-time cannot be extended indefinitely into the past. This mathematical peculiarity allows for an eternally existing multiverse without requiring an infinite past, a concept that transcends our conventional understanding of beginnings and causes. Similarly, in quantum cosmology, particularly the no-boundary proposal developed by James Hartle and Stephen Hawking, the origin of the universe is described not as an event in time, but as a boundary condition on the universal wave function. Time itself emerges from this quantum state, rather than existing prior to it. Asking what caused this quantum state becomes problematic, because causation implies temporal sequence, and time itself is part of what emerges from the quantum state, rather than a pre-existing framework within which the universe appears. In both these models, the traditional why question, seeking causes that preceded the universe, breaks down because the concept of before the universe loses meaning. Time is not an external container within which the universe exists, but a dimension of the universe itself, emerging along with space, matter, and energy. As the physicist Julian Barber puts it, the universe does not exist in time, time exists in the universe. Another framework that challenges traditional why questions comes from mathematical or structural realism, the view that the fundamental nature of reality is mathematical or structural rather than physical in the conventional sense. In this perspective, developed by philosophers like James Ladyman and Don Ross and physicists like Max Tegmark, the universe exists because it corresponds to a mathematical structure, with physical reality representing one manifestation of abstract mathematical relationships. This mathematical universe hypothesis suggests that any mathematically consistent structure exists in the same sense that our universe exists, with our particular universe corresponding to one such structure. The question, why does our universe exist, transforms into, why does this mathematical structure exist? And since mathematical structures exist necessarily, rather than contingently, they require no further explanation. 2 + 2 = 4, not because something made it so, but because it could not be otherwise, given the definitions and axioms of arithmetic. If physical reality is fundamentally mathematical in this sense, then the existence of the universe might similarly require no further explanation. It would exist because it corresponds to a consistent mathematical structure, and such structures exist necessarily rather than contingently. The universe would not need a cause or creator, any more than mathematical truths need causes or creators. It would simply be. This perspective connects to what philosophers call the principle of sufficient reason, developed by Gottfried Wilhelm Leibniz, which holds that everything must have a reason or cause for why it is as it is rather than otherwise. When applied to the universe as a whole, this principle leads to the question, why is there something rather than nothing? Leibniz concluded that the answer must lie in a necessary being, God, whose existence is self-explaining. The mathematical universe hypothesis offers a different resolution to this question. If mathematical structures exist necessarily rather than contingently, and if the universe is fundamentally a mathematical structure, then its existence would also be necessary rather than contingent. The universe would exist because it could not exist, given the necessary existence of the mathematical structure that constitutes it. The something would be necessary, making nothing impossible rather than merely unrealized. This mathematical perspective transforms how we understand explanation itself. Typically, we explain things by showing how they follow from more fundamental principles or causes. But if the universe corresponds to a fundamental mathematical structure, there might be nothing more fundamental from which it could be derived. It would represent a kind of explanatory bedrock, not because our knowledge is limited, but because the concept of a more fundamental explanation breaks down at this level. The physicist Sean Carroll has developed a related perspective, suggesting that the universe might be best understood as existing without causal anchoring in a more fundamental reality. In his view, the cosmos simply is, with its existence representing a brute fact that requires no further explanation. The laws of physics describe how the universe evolves over time, but they do not and cannot explain why these particular laws exist or why there is a universe at all. Carroll argues that this is not an admission of defeat, but a recognition of the limits of certain types of explanation. Just as we eventually reach bedrock when asking why questions in other domains, the universe itself might represent the ultimate explanatory bedrock, the point beyond which certain forms of why questions no longer apply. This would not mean giving up on understanding the universe, but recognizing that understanding may take forms different from our everyday explanatory practices. This perspective resonates with the philosophical position known as naturalism, which holds that reality consists only of natural entities and processes, with no supernatural or transcendent realities beyond the natural world. In a naturalistic framework, the universe itself represents the ultimate reality, not a creation of or dependent upon something beyond itself. The cosmos would be self-contained and self-sufficient, existing without requiring or allowing explanation in terms of anything outside itself. The philosopher David Hume captured a similar insight in the 18th century when he noted that while we can explain any particular thing within the universe by reference to other things, we cannot apply the same logic to the universe as a whole. The universe, being all there is, cannot be explained by reference to something outside itself, without contradicting the very definition of universe as all-encompassing. This suggests that the why question, asking for reasons external to the thing being explained, breaks down when applied to the totality of existence. Some scientists and philosophers have described this perspective as a form of cosmic humility, an acceptance that certain forms of questioning, though deeply ingrained in human cognition, may not apply to reality at its most fundamental level. Just as we had to abandon the intuitive, geocentric model of the cosmos, with Earth at the center of creation, we may need to abandon the intuitive notion that everything, including the universe itself, must have a cause or reason outside itself. This humility does not mean abandoning the quest to understand the cosmos. On the contrary, it redirects this quest from potentially unanswerable why questions to more productive how questions. Rather than asking why the universe exists, we might ask how it evolved from its initial state, how its laws operate, how complexity emerged from simplicity, how consciousness arose from unconscious matter. These questions remain open to scientific investigation even if the ultimate why question exceeds the scope of the scientific method. The physicist Richard Feynman expressed a similar sentiment when asked to explain magnetic attraction in a television interview. After initially explaining that magnetism results from the exchange of photons, he acknowledged that any explanation eventually leads to a point where we have to say, this is just how nature is. We have developed a mathematical structure that describes it, but we cannot offer a more fundamental why. Feynman emphasized that recognizing this limit is not anti-scientific but deeply scientific, an acceptance that understanding nature means developing models that describe and predict phenomena, even if these models eventually reach a point where no more fundamental explanation is possible or meaningful. The why question, seeking reasons beyond the most fundamental laws we can discover, might simply have no answer that would satisfy human intuition. This perspective connects to the concept of explanation itself and how it functions in different domains. In everyday life, we explain events by placing them in a broader context, showing how they fit into causal sequences or larger patterns. But this approach assumes an external context within which the thing being explained exists. The universe as a whole, by definition, has no external context. It encompasses everything that exists physically, leaving nothing outside itself to serve as an explanatory framework. Some philosophers of science, including Nancy Cartwright and James Woodward, have developed accounts of explanation that emphasize intervention and manipulation. We explain phenomena by identifying factors that, if manipulated, would change the outcome. This interventionist approach works well for particular systems within the universe, but breaks down when applied to the universe as a whole, since there is no outside position from which to intervene in or manipulate the totality of existence. Similarly, unification accounts of explanation, which see understanding as the integration of diverse phenomena under more general principles, face challenges when applied to the universe as a whole. If the universe encompasses everything that exists physically, there can be no more general domain of which it is a part, no more fundamental principles from which its existence could be derived. It would represent the ultimate domain of unification, beyond which the concept of unifying separate domains loses meaning. These considerations suggest that the very concept of explanation, as traditionally understood, might break down when applied to existence itself. Explanation typically involves showing how something fits into a larger pattern or follows from more fundamental principles. But the universe as a whole is the largest possible pattern, encompassing everything that exists physically. And the most fundamental physical laws, whatever they may be, would not follow from anything more fundamental by definition. They would represent the explanatory bedrock, the principles that explain other things, but are not themselves explicable in terms of anything deeper. This insight has led some philosophers to propose a shift in how we think about cosmic explanation. Rather than seeking reasons for existence outside existence itself, we might recognize that the universe explains itself from within, through its internal patterns, symmetries, and relationships. The cosmos would not require an external reason or cause, but would be self-explaining and self-sustaining, with each part explained by its relationships to other parts within the whole. The philosopher Timothy O'Connor has developed a related perspective, suggesting that explanation need not always involve showing how something follows from prior conditions or more fundamental principles. Some realities might be self-explaining, their existence following necessarily from their nature rather than from external causes. This concept of metaphysical necessity offers a way to think about the universe as self-explaining without requiring causes outside itself. If the universe exists necessarily rather than contingently, its existence would not require explanation in terms of something else. It would simply be the kind of thing that could not exist, its non-existence representing a logical or metaphysical impossibility, rather than merely an unrealized possibility. The why question would be answered not by identifying external causes or reasons, but by recognizing the internal necessity of existence itself. This perspective resonates with certain religious and philosophical traditions, while transforming them in light of modern physics. Some mystical traditions speak of existence as self-causing and self-sustaining, a reality that emanates from itself rather than from something outside itself. The philosopher Spinoza described what he called God or nature as a necessarily existing substance that produces itself and all things from its own essence, requiring no external creator or cause. Modern physics gives new meaning to these ancient intuitions, suggesting mathematical frameworks in which the universe might indeed exist necessarily rather than contingently, its existence following from its internal structure rather than from external causation. The why question would be answered not by looking beyond the universe for its creator or cause, but by understanding the necessity inherent in its mathematical or logical structure. This self-explaining universe would not require an appeal to brute facts or a rejection of rational inquiry. On the contrary, it would represent the ultimate fulfillment of rational explanation, a reality that makes sense in terms of itself rather than requiring reference to something beyond itself. The cosmos would be intelligible not because it was designed by an external intelligence, but because its internal structure embodies mathematical and logical principles that rational minds can discover and understand. This perspective transforms traditional questions about cosmic origins. Rather than asking what caused the universe, assuming that it requires an external cause, we might ask how the universe generated itself through its internal dynamics, how time and causality themselves emerged from more fundamental principles, how complexity and structure evolved from simpler states. These questions remain open to scientific investigation, even if the ultimate why question transcends the scope of science as traditionally understood. Some physicists have suggested that the very laws of physics might themselves be emergent rather than fundamental, arising from deeper mathematical or informational principles through a kind of cosmic self-organization. In such a framework, developed by researchers like Fotini Markopoulou and Carlo Rovelli, both general relativity and quantum mechanics, our most fundamental physical theories, would emerge from more basic relational or informational dynamics. If correct, this would mean that even our most basic physical laws would be explained not by reference to something outside physics, but by showing how they emerge naturally from deeper patterns within physics itself. The why question, asking for reasons beyond physics, would be replaced by how questions exploring the emergence of physical law from within the cosmic system, rather than from outside it. This emergent perspective connects to broader questions about levels of explanation in science and whether different levels can be reduced to more fundamental ones. Traditionally, physics has been seen as the most fundamental science, with chemistry, biology, psychology, and other disciplines building on this foundation. But some philosophers of science, including Nancy Cartwright and John Dupre, have challenged this hierarchical view, suggesting that different sciences describe reality at different levels, with no level being more fundamental or real than others. Applied to cosmic origins, this anti-reductionist perspective suggests that questions about why the universe exists might not be answerable by reducing everything to physics or mathematics. The various levels of explanation, from physics to chemistry to biology to psychology and beyond, might each capture something real about the cosmos that cannot be reduced to or replaced by explanations at other levels. The universe would explain itself not through a single fundamental theory, but through the interplay and integration of multiple levels of explanation, each valid in its domain. This multi-level perspective connects to what philosopher William James called pragmatism, the view that truth is what works in practice, rather than what corresponds to some external reality, independent of our investigations. From a pragmatic standpoint, the question of why the universe exists might be evaluated not by whether it leads to the metaphysical truth, but by whether asking it leads to productive insights and practical advances in understanding. By this standard, the why question has certainly been productive throughout human history, driving scientific, philosophical, and religious inquiry that has expanded our understanding of reality. But it may reach a point of diminishing returns when applied to the ultimate origin of everything, a point where the question itself becomes more of a hindrance than a help to further understanding. The physicist Victor Stenger captured this pragmatic perspective when he suggested that the question, "Why is there something rather than nothing?" assumes that nothing is the natural state from which something must be explained as a deviation. But, Stenger argued, there is no reason to privilege nothing over something as the default state of reality. If both something and nothing are possible states, and if something clearly exists, as evidenced by our existence, then perhaps nothingness is the state that would require explanation rather than existence. This inversion of the traditional question highlights how much our asking depends on implicit assumptions about what is natural or default versus what requires explanation as a deviation from the default. These assumptions are not given by reality itself, but reflect human cognitive tendencies and cultural frameworks. The sense that existence itself requires explanation might reflect these tendencies rather than a metaphysical truth about reality. The philosopher Ludwig Wittgenstein explored this territory from another angle, suggesting that certain philosophical problems arise not from reality itself, but from confusions in how we use language. The seemingly sensible question, "Why does anything exist at all?" might actually contain linguistic confusions that make it unanswerable in principle, like asking what the color of jealousy smells like. Such questions can be grammatically correct, but semantically problematic, using concepts in domains where they do not properly apply. From a Wittgensteinian perspective, the why question applied to existence itself might involve a misapplication of concepts that work within the universe to the universe as a whole. The concept of explanation, as we typically use it, assumes an explanatory framework outside or more fundamental than the thing being explained. But the universe as a whole, being all-encompassing by definition, has no outside or more fundamental framework. The question itself might involve a conceptual confusion rather than pointing to a genuine mystery about reality. This linguistic perspective does not dismiss the deep human drive to understand cosmic origins, but suggests that this drive might need to express itself through questions different from the traditional why. Rather than asking why anything exists at all, we might ask how existence manifests in its diverse forms, how complexity emerges from simplicity, how consciousness arises from physical processes. These questions align better with how language and concepts actually function than the ultimate why question, which strains language and concepts beyond their proper domains. As we reflect on these diverse perspectives suggesting that asking why the universe exists might be meaningless or misconceived, we recognize that we stand at a profound frontier of human understanding. The universe appears to be not only stranger than we suppose, but stranger than we can suppose. A reality whose ultimate nature may transcend the categories of our thought, while remaining accessible to our mathematical description and scientific investigation. This recognition does not diminish the wonder of existence, but transforms it. The wonder is not that something impossible or highly improbable occurred, requiring supernatural intervention, but that reality itself contains the principles of its own existence, a cosmos that creates and sustains itself through internal necessity, rather than external causation. The traditional why question, asking for reasons beyond existence, gives way to an appreciation of the internal intelligibility of existence itself, a reality that makes sense in terms of itself, rather than requiring reference to something beyond itself. As the physicist Brian Greene puts it, the universe is under no obligation to make sense to human intuition or to conform to human categories of thought. The fact that reality turns out to be far stranger and more wonderful than our everyday experience suggests does not mean that it is ultimately unintelligible. On the contrary, the mathematical and logical structures that modern physics reveals in the cosmos suggest a deeper intelligibility than our ancestors could have imagined, a reality whose internal coherence and necessity we continue to discover through scientific investigation. This perspective offers a kind of cosmic liberation. Rather than requiring the universe to justify its existence through causes or purposes beyond itself, we recognize that it contains the principles of its own existence within itself. The cosmos would not be created by something outside itself, but would create itself through its internal dynamics, a self-sustaining and self-explaining system that requires no external creator or cause. This self-creating, self-explaining universe would not eliminate mystery, but transform it. The wonder would be not that something came from nothing through external intervention, but that reality itself contains the principles of its own existence, a cosmos whose internal structure embodies mathematical and logical necessity rather than contingency or arbitrariness. As we continue our exploration, we will examine whether the laws of physics themselves might be inevitable rather than arbitrary, whether the fundamental constants of nature might be determined by deeper principles rather than set by chance or design. We will consider whether the apparent fine-tuning of physical constants might be explained through cosmic self-organization, quantum selection, or other natural processes. In these investigations of cosmic necessity and self-determination, we may find further clues to how a universe might create itself, not through external causation but through internal necessity and self-consistency. We began our journey with a question that has echoed through human history: how did the universe create itself? We have traveled from the first fraction of a second after the Big Bang to the farthest reaches of cosmic time and space. We have explored quantum foam and virtual particles, emergent time and infinite multiverses, conscious observation, and self-generating laws. Throughout this odyssey, we have encountered a cosmos far stranger and more wonderful than our ancestors could have imagined, a reality whose capacity for self-creation appears woven into its very fabric. As we draw the threads of our exploration together, we find not a single simple answer to our question, but a tapestry of interwoven insights that together suggest how a universe might indeed create itself, not through external intervention, but through processes inherent in the nature of reality itself. From quantum mechanics, we learn that the vacuum is never truly empty, but teems with virtual particles, flickering briefly into existence before disappearing again. These quantum fluctuations, governed by the uncertainty principle, suggest that nothingness itself is unstable, naturally generating complexity through the mathematical principles that govern quantum reality. The seemingly empty void contains the seeds of everything, an inherent creative potential embedded in the very structure of quantum fields. From general relativity and cosmology, we discovered that the total energy of a universe with flat geometry, like our own, might sum precisely to zero, with the positive energy of matter and radiation balanced by the negative gravitational energy of space. This zero-energy balance allows a universe of vast size and complexity to arise without violating conservation principles, requiring no net energy input from outside. The cosmos might truly be the ultimate free lunch, emerging naturally from quantum nothingness through processes that require no external input or power source. From studies of cosmic inflation, we encountered the possibility that our universe might be one bubble in an eternally inflating multiverse, with new bubble universes continually forming through quantum processes in the expanding space. This would transform the creation of our universe from a singular, unique event requiring external causation to one instance of a natural, ongoing process occurring throughout the multiverse. Our cosmic home would not be specially created, but would emerge through the same quantum processes that generate countless other universes across the infinite reaches of the multiverse. From loop quantum cosmology and cyclic models, we explored how our universe might have emerged, not from nothing but from the collapse of a previous universe, with the apparent Big Bang singularity replaced by a quantum bounce. This would extend cosmic history far beyond the 13.8 billion years we can directly observe, suggesting that the universe continually recreates itself through cycles of expansion, collapse, and rebirth. Creation would not be a one-time event, but an ongoing process of cosmic renewal, with each cycle emerging naturally from the previous one through quantum gravitational processes that require no external cause or intervention. From investigations of the observer effect in quantum mechanics, we encountered the possibility that consciousness and observation might play deeper roles in cosmic evolution than previously imagined. The participatory universe concept, developed by physicist John Wheeler, suggests that the universe exists as quantum potential until observed, with observers themselves emerging from this potential through a kind of cosmic self-observation. The universe would not be created by something outside itself, but would create itself partially through being observed and understood by the conscious beings it produces, a kind of cosmic bootstrap operation where existence emerges through self-observation. From considerations of why questions and their limits, we recognize that asking what caused the universe might be misleading if time itself began with the universe, leaving no before in which a cause could operate. The universe might not require a cause or explanation outside itself, but might be self-explaining through its internal structure and dynamics. Creation would not be an event in time, but a timeless principle inherent in the mathematical structure of reality itself. And from explorations of physical law and its origins, we encountered the possibility that the constants and principles governing our universe might not be arbitrary, but inevitable, emerging naturally from deeper principles of symmetry, mathematical consistency, or self-organization. The cosmos would create not only itself, but its own rules through internal dynamics rather than external imposition, a universe that is self-determining in the deepest possible sense. These diverse perspectives together suggest a universe that creates itself through natural processes of quantum fluctuation, inflation, bounce, observation, and self-organization, a cosmos that emerges not from external causation, but from principles inherent in the nature of reality itself. Creation would not be an event in the distant past, but an ongoing process in which we participate through our observations and our quest to understand. This self-creating universe transforms how we understand our place in the cosmos. Rather than being accidental byproducts of blind physical processes or the intended outcomes of a pre-existing plan, conscious beings would be integral to the universe's self-creation and self-understanding. Consciousness would not be an epiphenomenon, a mere side effect of physical processes, but a fundamental aspect of cosmic evolution, a means by which the universe observes itself and thereby establishes its own nature and history. In this participatory cosmos, our scientific quest to understand the universe would be not merely the accumulation of knowledge about an external reality, but part of how the universe comes to know itself, to create itself, through the conscious beings it has produced. Every observation of distant galaxies, every experiment probing quantum reality, every mathematical insight into cosmic structure would represent the universe exploring its own nature and possibility, creating itself partially through self-observation and self-understanding. This perspective does not eliminate mystery but transforms it. The wonder is not that something impossible occurred, requiring supernatural intervention, but that the fabric of reality itself contains the potential for its own creation and evolution. The universe may be self-creating, self-organizing, and self-determining, a manifestation of the creative potential inherent in quantum reality, mathematical structure, and conscious observation. As the physicist Freeman Dyson puts it, the more I examine the universe and the details of its architecture, the more evidence I find that the universe, in some sense, must have known we were coming. The laws of nature seem remarkably well designed to allow for the emergence of complexity, consciousness, and observation. Rather than seeing this as evidence for an external designer, we might recognize it as a sign that the universe creates itself partially through becoming observable, through generating the conditions that allow it to witness and understand its own existence. The self-creating universe resonates with certain religious and philosophical traditions, while transforming them in light of modern physics. Many spiritual traditions speak of creation as ongoing rather than completed, of the divine as immanent within nature rather than separate from it, of consciousness as fundamental rather than emergent, of humanity as participating in rather than merely witnessing cosmic creation. The scientific vision of cosmic self-creation gives new meaning to these ancient intuitions, suggesting a universe that creates itself from within rather than being created from without. At the same time, this perspective honors the profound insights of modern science, from quantum uncertainty to cosmic inflation, from relativistic spacetime to quantum information. It integrates these discoveries into a cohesive vision of a universe whose capacity for self-creation arises not from miraculous intervention, but from the natural principles that govern quantum reality, gravitational physics, and complex systems. The cosmos would be self-creating, not through magic or miracle, but through the unfolding of its inherent potential, according to discoverable principles. As we conclude our cosmic journey, we recognize that our understanding remains incomplete. We stand not at the end of inquiry, but at a new beginning, with each answer generating fresh questions, each discovery revealing new mysteries. The question of how the universe created itself might never receive a final, definitive answer, but might continue to deepen and evolve as our knowledge expands and our perspective broadens. Yet even in this ongoing quest, we glimpse a profound possibility, a universe that creates itself through its own unfolding logic, a cosmos that emerges not from external causation but from principles inherent in the fabric of reality itself. In place of creation from outside, we find creation from within. In place of design imposed from above, we discover order emerging from below. In place of a universe made by something else, we encounter a universe making itself. Perhaps the greatest wonder of all is not that the universe was created, but that it creates itself, not once but continually, through processes that unite necessity and creativity in the ongoing dance of cosmic becoming. We exist not in a finished creation, but in a universe, still creating itself, still discovering its own nature and possibility, still expanding not only in space, but in complexity, consciousness, and understanding. In the stillness between stars, in the quantum foam of empty space, in the mathematical symmetries that govern reality, in the conscious minds that contemplate existence, we find not a creator separate from creation, but creation itself, the universe emerging from its own inherent potential, through principles that unite matter and mathematics, chaos and order, being and becoming. The cosmos may not have emerged from something. It may not have been made by anything. It may have arisen because it could, and in that quiet possibility lies the greatest wonder of all. As our cosmic journey comes to a close, we find ourselves standing at the threshold of a new understanding, a vision of reality that integrates the deepest insights of modern physics with our most profound philosophical questions. The universe as self-creating system represents not an end to our inquiry, but a beginning, a framework that generates new questions even as it addresses old ones. Let us expand our perspective further, exploring additional dimensions of cosmic self-creation and their implications for our understanding of existence itself. The concept of emergence threads through our entire exploration, the way complex patterns and behaviors arise from simpler foundations through natural processes. We see emergence at every scale in nature, from the way particles combine to form atoms, atoms to form molecules, molecules to form cells, cells to form organisms, and organisms to form societies. At each level, new properties appear that could not have been predicted from the components alone, with the whole becoming more than the sum of its parts. This emergence principle may extend to the fundamental nature of reality itself. Space, time, matter, energy, and even the laws of physics might emerge from more basic patterns or processes, perhaps from networks of quantum relationships or flows of information. What we experience as physical reality might be an emergent structure, arising from a more fundamental substrate that itself has no spatial, temporal, or material qualities as we understand them. Physicist Carlo Rovelli captures this perspective in his relational interpretation of quantum mechanics, which suggests that physical properties exist, not absolutely, but only in relation to other systems. A particle does not have an intrinsic position, but exists in different positions relative to different reference frames. Applied to the cosmos as a whole, this relational view suggests that the universe exists not as an absolute entity, independent of relationships, but as a network of interactions, with reality emerging from the totality of these relationships rather than existing prior to them. This emergent relational cosmos would be self-creating in a profound sense. It would not exist first and then develop relationships between its parts, but would continually create itself through these relationships. The universe would be not a thing but a process, not a noun but a verb, continually becoming rather than statically being. Creation would not be an event in the past, but the ongoing process by which reality manifests from moment to moment through the web of relationships that constitute existence itself. This process perspective resonates with certain philosophical traditions, particularly the process philosophy of Alfred North Whitehead and the pragmatism of William James. Whitehead described reality as composed not of enduring substances but of events or occasions, each representing a creative advance into novelty. The cosmos would not be a collection of objects moving through time, but a series of interconnected events, each emerging from and contributing to the whole in a continuous process of becoming. Applied to cosmic origins, this process view suggests that the universe did not come into being at a specific moment as a completed entity, but continually creates itself through an ongoing process of cosmic becoming. The Big Bang would not mark the beginning of everything but one phase in this endless process of creative advance, a particularly dramatic moment in the continuous emergence of reality from possibility. This endless creativity connects to what philosophers call the principle of plenitude, the idea that all genuine possibilities are ultimately realized somewhere, sometime. Physicist Hugh Everett's many worlds interpretation of quantum mechanics gives this ancient philosophical principle new meaning, suggesting that reality branches at each quantum event, with all possibilities manifesting in different branches of an ever-dividing cosmic tree. The universe would not select one possibility from many, but would realize all possibilities across the branches of quantum reality, an ultimate expression of creative plenitude that leaves nothing unmanifested. This perspective transforms how we understand possibility itself. In conventional thinking, possibilities represent alternatives, with only one becoming actual, while the others remain merely potential. But in the many worlds framework, all genuine possibilities become actual, each in its own branch of reality. There would be no merely potential states, only actual states in different branches of the quantum multiverse. The cosmos would express not only what did happen, but what could have happened, a complete manifestation of possibility itself. If reality does indeed encompass all possibilities in this way, this would represent the ultimate form of cosmic self-creation. The universe would not merely create itself once, in one particular form, but would create itself in all possible forms, leaving no potential unexpressed, no possibility unrealized. Creation would not be a selection of one reality from many possibilities, but the manifestation of all possibilities across the branching structure of quantum reality. This vision of cosmic plenitude connects to what mathematicians call the principle of computational equivalence, developed by scientist Stephen Wolfram, which suggests that above a certain threshold of complexity, all systems are capable of the same level of computational sophistication. Applied to cosmic evolution, this suggests that once the universe reaches a certain level of complexity, it can generate all possible computational structures, including consciousness and even artificial universes simulated within the larger cosmic system. The possibility of simulated universes adds another dimension to cosmic self-creation. If sufficiently advanced civilizations can create detailed simulations of their own universe or other possible universes, then reality might include multiple levels of simulation, with simulated universes containing their own simulated universes, and so on. Philosopher Nick Bostrom has suggested that if such simulations are possible, there might be far more simulated universes than base reality universes, making it statistically likely that our own reality is itself a simulation within a larger cosmic system. This nested simulation scenario would represent another form of cosmic self-creation, with the universe generating new universes through the conscious beings it produces. Creation would flow not from outside the system, but from within it, with universes emerging from the computational processes of the civilizations they contain. The cosmos would create itself not only through physical processes like quantum fluctuations and inflation, but through computational processes emerging from the complex systems the universe itself generates. The computational perspective connects to broader questions about information and its role in physical reality. Physicist John Wheeler captured this in his phrase "it from bit," suggesting that what we experience as physical reality emerges from more fundamental informational processes. In this view, the universe does not contain information as one aspect among many, but is fundamentally informational, with matter, energy, space, and time representing different manifestations of underlying informational patterns and processes. Recent work in quantum information theory supports this informational perspective, suggesting deep connections between quantum entanglement, the holographic principle, and the emergence of spacetime itself. Research by theorists like Juan Maldacena indicates that spacetime geometry might emerge from quantum entanglement, the non-local correlations between quantum systems. Space itself would not be a fundamental container within which physics happens, but a structure that emerges from more basic quantum information processes. If spacetime itself emerges from quantum information in this way, this would transform our understanding of cosmic origins. The creation of the universe would not be the sudden appearance of a spatial and temporal reality from nothing, but the emergence of space and time, from a more fundamental informational reality that itself has no spatial or temporal qualities as we understand them. The cosmos would create itself not in space and time, but as space and time, with the familiar four-dimensional spacetime of our experience emerging from a more fundamental reality beyond space and time as we know them. This emergence of spacetime connects to what physicists call non-commutative geometry, mathematical frameworks where space has a quantum structure at the smallest scales, with spatial coordinates that do not commute when multiplied, like quantum operators. In these frameworks, developed by mathematicians like Alain Connes, spacetime itself becomes quantum and fuzzy at the Planck scale, with the familiar continuous space of our experience emerging only at larger scales where quantum effects average out. If space itself has this quantum, non-commutative structure at the fundamental level, this suggests a universe that creates itself through quantum processes, not occurring within space but creating space itself. The fabric of reality would not exist first, and then develop patterns within it, but would emerge from more fundamental quantum patterns and relationships. The cosmos would create not only its contents, but its very container, through natural quantum processes that require no external cause or explanation. These insights about the emergence of space-time connect to philosophical traditions that question the ultimate reality of space and time. Philosopher Immanuel Kant described space and time not as features of reality in itself, but as forms of human perception, the way our minds organize experience rather than independently existing dimensions. This idealist perspective finds new expression in certain interpretations of quantum mechanics, where the wave function of the universe might exist in a realm beyond space and time as we experience them, with our familiar four-dimensional reality emerging through observation and measurement. The physicist Donald Hoffman has developed this perspective through what he calls the interface theory of perception, which suggests that our experience of space-time represents an interface adapted for survival, rather than an accurate representation of fundamental reality. Just as a computer desktop with its icons and folders provides a user-friendly interface to computational processes that bear little resemblance to these visual metaphors, our experience of space, time, and objects might provide a user-friendly interface to a reality far stranger than our perceptions suggest. If Hoffman is right, and our perception of space-time represents an evolved interface rather than fundamental reality, this would further transform our understanding of cosmic self-creation. The universe would create not only itself, but our perception of itself through the evolutionary processes that shaped consciousness. What we experience as reality would represent not the universe as it is in itself, but the universe as filtered through perceptual systems, evolved for survival, rather than for accurate metaphysical representation. This perspective on perception connects to broader questions about the role of the observer in quantum reality. As we explored earlier, the observer effect in quantum mechanics suggests that measurement plays a crucial role in determining physical reality, with quantum systems existing in states of possibility rather than actuality until observed. Applied to the cosmos as a whole, this suggests a universe that creates itself partially through being observed, with observation helping to transform quantum possibilities into actualities. But what constitutes an observation, or measurement, in quantum terms? This question remains one of the most contested in quantum foundations. Some interpretations, like the Copenhagen interpretation, treat measurement as a primitive concept that cannot be further analyzed within the theory. Others, like the decoherence approach, suggest that measurement occurs when a quantum system interacts with its environment in ways that spread information about its state, making certain quantum superpositions practically unobservable. Recent work by physicist Wojciech Zurek on what he calls quantum Darwinism extends the decoherence approach, suggesting that the classical world of our experience emerges from quantum reality through a kind of natural selection process. Quantum states that can imprint multiple copies of themselves on the environment, making their information widely available, are naturally selected for observation, while states that cannot proliferate information in this way remain hidden in the quantum realm. The classical world would emerge from the quantum world not through conscious observation specifically, but through the natural selection of stable, replicable information patterns. This information-based perspective suggests a universe that creates itself through the proliferation and selection of information, with stable, observable patterns emerging naturally from quantum possibilities through interaction with the environment. The cosmos would not require conscious observers to collapse quantum states, but would select observable states naturally through the dynamics of information transfer and replication. Consciousness would participate in this process, but would not be fundamentally responsible for the emergence of classical reality from quantum potentiality. The quantum Darwinism approach connects to broader themes of selection and evolution in cosmic self-creation. Throughout our exploration, we have encountered selection processes operating at various scales, from the selection of vacuum states in the inflationary multiverse to the selection of physical constants through cosmic natural selection, from the selection of observable quantum states through decoherence to the selection of conscious observers through biological evolution. These nested selection processes suggest a universe that creates itself through multiple levels of variation and selection, with each level building on and emerging from the previous ones. This multi-level selection perspective offers a unified framework for understanding cosmic self-creation, integrating quantum processes, inflation, gravitational physics, chemistry, biology, and consciousness within a coherent vision of nested creative processes. The universe would create itself not through a single mechanism, but through multiple interconnected processes of variation and selection operating at different scales and levels, from the quantum to the cosmic, from the physical to the biological, to the conscious and cultural. Such a framework avoids both extreme reductionism, which attempts to explain everything in terms of the smallest components, and extreme holism, which treats the whole as fundamentally irreducible to its parts. Instead, it recognizes multiple levels of organization and causation, with each level both emerging from and constraining the levels below it in a complex dance of bottom-up and top-down causation. The cosmos would create itself through this interplay between levels, with neither the smallest nor the largest scale having absolute primacy in the creative process. Philosopher Paul Davies captures this multi-level perspective in what he calls the Goldilocks enigma, the observation that the universe appears fine-tuned not just for existence, but for the emergence of complexity across multiple scales. From the subatomic to the cosmic, the parameters of our universe seem carefully calibrated to allow for the emergence of atoms, stars, planets, chemistry, biology, and eventually consciousness. This calibration might reflect not a pre-existing design but the outcome of selection processes operating across the multiverse, a kind of cosmic learning through which universes gradually discover the conditions that maximize complexity and self-observation. This learning perspective connects to what computer scientists call evolutionary computation, the use of variation and selection principles to discover solutions to complex problems without explicit programming. Applied to cosmic evolution, this suggests that the universe might discover the principles of its own existence and development, not through external guidance, but through internal processes of variation, selection, and replication, operating across vast scales of space, time, and possibility. The cosmos would learn how to create itself through a kind of cosmic computation that requires no programmer or external input. The evolutionary computing model offers yet another framework for understanding cosmic self-creation, one that integrates information, computation, and selection within a coherent vision of a self-organizing cosmos. The universe would create itself through computational processes analogous to those we observe in evolutionary systems, discovering effective patterns and principles through exploration of possibility space, rather than through predetermined design or external guidance. This computational perspective connects to what physicists call algorithmic information theory, which measures the complexity of a system by the length of the shortest computer program that could generate it. Applied to the cosmos, this suggests that the universe might be extraordinarily complex in its details, while being relatively simple in its generative principles, like a fractal pattern that produces infinite complexity from a compact mathematical formula. The universe would create itself through the operation of relatively simple, algorithmic processes that generate vast complexity through their repeated application and interaction. Mathematician Gregory Chaitin has extended this approach through what he calls metabiology, the exploration of abstract models of evolution based on algorithmic information theory. His work suggests that evolution represents a kind of creative mathematics, a process that discovers new patterns and principles through variation and selection rather than through deductive proof. Applied to cosmic evolution, this suggests that the universe might create itself through a similar process of creative exploration, discovering its own principles through a kind of cosmic computation that generates complexity from simplicity, order from chaos, being from becoming. This creative, evolutionary cosmos connects to what philosopher Daniel Dennett calls the strange inversion of reasoning, the way certain natural processes create results that appear designed without requiring a designer. Evolution by natural selection represents the paradigmatic example, generating adaptations so intricate they seem purposefully crafted, yet requiring no conscious planning or foresight. Applied to cosmic self-creation, this suggests that the apparent design we observe in physical law and cosmic structure might emerge naturally from evolutionary processes operating at the universal scale, without requiring external design or guidance. The strange inversion extends beyond biology to other self-organizing processes throughout nature, from the formation of snowflakes to the emergence of galactic structures, from the development of language to the evolution of culture. At every level, complex, ordered patterns emerge from simpler foundations through natural processes that require no conscious direction or control. The cosmos would create itself through these self-organizing dynamics, with complexity and order emerging naturally from simplicity and chaos through principles of variation, selection, and replication operating across all scales. This self-organizing, evolutionary perspective transforms traditional questions about purpose and meaning in the cosmos. Rather than asking whether the universe has a purpose imposed from outside, we might ask how purposes emerge naturally within the universe through evolutionary processes. Purposes would not precede the cosmos, but would emerge within it as conscious beings evolve and develop their own goals, values, and meanings. The universe would not be designed for a purpose, but would generate purposes from within through the conscious beings it produces. Philosopher Thomas Nagel explores this territory in his book Mind and Cosmos, arguing that any complete theory of reality must account not only for physical phenomena, but also for the emergence of mind, consciousness, value, and reason. If these mental and normative aspects of reality are as real as the physical aspects, then our understanding of cosmic origins must explain not only how matter and energy came to exist, but how consciousness, value, and reason emerged as well. The self-creating cosmos would need to generate not only physical structure, but mental and normative structure too, a universe that creates not only matter, but meaning. Nagel suggests that this might require a kind of natural teleology, principles that guide cosmic evolution towards certain outcomes without involving conscious planning or external design. Such principles would not reflect purposes imposed from outside, but would be built into the structure of reality itself, natural tendencies toward the emergence of complexity, consciousness, and value. The universe would create itself according to principles that naturally lead toward these outcomes, not because they were planned in advance, but because they represent natural developments of the cosmic process itself. This natural teleology connects to what some philosophers call the fine-tuning of not just physical constants, but of natural laws and principles themselves. The laws of nature seem remarkably well suited, not just for the existence of matter, but for its organization into complex systems capable of computation, representation, and eventually consciousness. This higher-level fine-tuning might reflect not coincidence or design, but the outcome of selection processes operating across the multiverse, with universes that generate complexity and consciousness, representing attractors in the space of possible cosmic configurations. The attractor concept, borrowed from complex systems theory, offers another framework for understanding cosmic self-creation. Attractors represent states or patterns toward which dynamic systems naturally evolve, like a marble settling to the bottom of a bowl, regardless of where it starts. Applied to cosmic evolution, this suggests that certain configurations, such as universes that generate complexity and consciousness, might represent attractors in the space of possible universes, states toward which cosmic evolution naturally tends through processes of variation and selection. If complexity and consciousness represent attractors in this way, this would explain the apparent fine-tuning of our universe without requiring either extraordinary coincidence or conscious design. The universe would have the properties it does not because they were precisely calibrated from the beginning, but because these properties represent attractors toward which cosmic evolution naturally tends, states that maximize certain values like complexity, stability, and self-observation. The cosmos would create itself by discovering and actualizing these natural attractors through processes of variation and selection operating across the multiverse. This attractor perspective connects to what complexity theorists call self-organized criticality, the tendency of complex systems to evolve toward critical states balanced between order and chaos, states that maximize both stability and adaptability. The canonical example is a sand pile that naturally evolves toward a critical state, where additional grains trigger avalanches of all sizes, from tiny shifts to system-wide reorganizations. Applied to cosmic evolution, this suggests that universes might naturally evolve toward critical states balanced between rigid order and chaotic disorder, states that maximize both stability and creative potential. If our universe exists in such a critical state, balanced between order and chaos, this would explain its remarkable capacity for both stability and creativity, its ability to maintain enduring structures while continually generating novelty. The cosmos would create itself by discovering and maintaining this critical balance, evolving towards states that maximize both order and possibility, structure and surprise, continuity and creativity. The universe would be neither completely deterministic nor completely random, but would exist at the creative edge between these extremes, the zone of maximal generative potential. This creative edge connects to what biologist Stuart Kauffman calls the adjacent possible, the set of possibilities that can be reached from the current state through a single transformation. As a system evolves, it continually expands its adjacent possible, opening new possibilities that did not exist before. Applied to cosmic evolution, this suggests that the universe continually creates not only itself but its own possibilities, expanding the space of what can happen next through its ongoing development. Creation would be not a one-time establishment of all possibilities, but the continual expansion of possibility itself through the cosmic evolutionary process. The expanding adjacent possible offers a framework for understanding how genuine novelty can emerge in a lawful universe. While the basic laws of physics might remain constant, the possibilities they generate expand as the universe develops, with new structures and dynamics becoming possible as complexity increases. Life, mind, culture, technology, and perhaps forms of organization we cannot yet imagine would represent not violations of physical law but expansions of cosmic possibility, genuinely new forms emerging from the creative cosmos as it explores its ever-expanding adjacent possible. This vision of an endlessly creative cosmos resonates with certain religious and spiritual traditions, while transforming them in light of modern science. Creator and creation would not be separate, with the creator standing outside creation, but would be integrated within a self-creating whole, a cosmos that generates itself through its own internal dynamics rather than through external intervention. The divine would not transcend nature, but would be immanent within it, expressed through the creative processes that generate complexity, consciousness, and meaning from within the cosmos rather than imposing them from without. Theologian Gordon Kaufman captures this perspective in what he calls biohistorical naturalism, a view that locates creativity and value within the natural evolutionary process, rather than in a supernatural realm beyond nature. In this view, what traditions have called God might be reconceived as the creativity inherent in the cosmos itself, the generative processes through which novelty, complexity, and meaning continually emerge within the universe. The divine would not create the world from outside, but would be the creativity through which the world creates itself from within. This naturalistic spirituality connects to what philosopher Ken Wilber calls the great nest of being, a vision of reality as composed of nested levels of organization and complexity, from matter to life to mind to spirit, with each level transcending and including the levels below it. In this framework, spirit would not exist separate from nature, but would represent the creative wholeness of the cosmic process itself, the generative mystery from which all forms emerge and to which all return. The universe would create itself through this nested creative process, with each level building on and emerging from the previous ones in an endless dance of transcendence and inclusion. The Great Nest perspective integrates insights from science, philosophy, and spiritual traditions within a unified vision of cosmic creativity and development. It avoids both scientific reductionism, which acknowledges only the material level of reality, and religious supernaturalism, which places the source of creativity entirely beyond the natural world. Instead, it recognizes creativity and value as inherent in the cosmic process itself, emerging naturally through the self-organizing dynamics of a universe that creates itself from within rather than being created from without. This integrated vision offers a middle path between the extremes of scientific materialism and religious supernaturalism, one that honors both the profound insights of modern science and the deep wisdom of spiritual traditions. It suggests a universe that is neither merely material nor supernaturally designed, but inherently creative, a cosmos that generates not only matter and energy, but life, mind, consciousness, and meaning through its own internal dynamics, rather than through external intervention or control. As we reflect on these diverse perspectives on cosmic self-creation, we recognize both the limits of our current understanding and the incredible progress we have made in comprehending the universe and our place within it. We stand not at the end of this journey, but at a new beginning, with each answer generating fresh questions, each discovery revealing new mysteries. The question of how the universe created itself might never receive a final, definitive answer, but might continue to deepen and evolve as our knowledge expands and our perspective broadens. Yet even in this ongoing quest, we glimpse a profound possibility, a universe that creates itself through natural processes of quantum fluctuation, emergence, evolution, and self-organization, a cosmos that comes into being not through external intervention, but through principles inherent in the nature of reality itself. Creation would not be an event in the distant past, but an ongoing process in which we participate through our observations, our scientific explorations, our philosophical reflections, and our conscious experience of being part of this vast, creative whole. This participatory cosmos transforms how we understand our place in the universe. Rather than being accidental byproducts of blind physical processes or the intended outcomes of a pre-existing plan, conscious beings would be integral to the universe's self-creation and self-understanding. Consciousness would not be an epiphenomenon, a mere side effect of physical processes, but a fundamental aspect of cosmic evolution, a means by which the universe observes itself and thereby establishes its own nature and history. We would be not merely in the universe, but of it, participants in its ongoing creation, rather than mere spectators of a completed work. In this self-creating cosmos, our scientific, philosophical, artistic, and spiritual explorations would represent not merely human activities, but cosmic processes, ways in which the universe comes to know itself, to create itself, through the conscious beings it has produced. Every scientific discovery, every philosophical insight, every artistic creation, every spiritual experience would manifest the universe exploring its own nature and possibility, creating itself partially through self-observation and self-understanding. Human creativity would be an extension of cosmic creativity, a local manifestation of the generative processes through which the universe continually creates itself. This perspective does not diminish human uniqueness or significance, but places it within a larger cosmic context, a universe that creates itself through the emergence of increasingly complex forms of organization and awareness. Human consciousness, with its capacity for self-reflection, abstraction, language, art, science, philosophy, and spiritual experience, would represent one particularly intricate expression of the cosmic creative process, a way for the universe to know itself with unprecedented depth and clarity. Our existence would be neither an accident nor a miracle, but a natural development of a cosmos inherently oriented toward the emergence of complexity and consciousness. As we conclude our journey, we return to the question with which we began: how did the universe create itself? We have explored diverse answers, from quantum fluctuations in the vacuum to eternal inflation, from cosmic bounces to participatory observation, from emergent time to self-organizing law. We have considered how a universe might create itself through principles inherent in quantum reality, mathematical structure, and conscious awareness. We have encountered a cosmos far stranger and more wonderful than our ancestors could have imagined, a reality whose capacity for self-creation appears woven into its very fabric. These diverse perspectives together suggest a universe that creates itself not once, but continually, not through external intervention, but through internal dynamics, not by chance or design, but through processes that unite necessity and creativity in the ongoing dance of cosmic becoming. We exist not in a finished creation, but in a universe, still creating itself, still discovering its own nature and possibility, still expanding not only in space, but in complexity, consciousness, and understanding. In the words of the poet William Blake, to see a world in a grain of sand, and a heaven in a wild flower, hold infinity in the palm of your hand, and eternity in an hour. As we contemplate the self-creating cosmos, we find infinity and eternity not in some realm beyond the physical universe, but in the endless creativity inherent within it, a universe that encompasses not only what is, but what could be and what might become, a cosmos of boundless potential continually actualizing itself through the ongoing miracle of existence itself. Perhaps the greatest wonder of all is not that the universe exists, but that it creates itself, that being emerges naturally from the fabric of reality through principles that unite matter and mathematics, chaos and order, necessity and possibility. In that quiet wonder lies an understanding more profound than any final answer, a recognition that we participate in the ongoing creation of a cosmos still discovering itself, still becoming what it has always had the potential to be, a universe creating itself from within through the endless dance of becoming that we call existence.